Azure Virtual Machines represents the foundation of Microsoft's Infrastructure as a Service (IaaS) offering, providing a flexible and powerful solution for organizations requiring granular control over their computing environment. This service model strikes a careful balance between customization capabilities and managed infrastructure, offering significant advantages over both traditional on-premises solutions and more managed cloud services. The IaaS model through Azure Virtual Machines delivers instant computing infrastructure, provisioned and managed over the Internet. This approach provides several key benefits: complete control over the operating system, ability to run any compatible software, customizable storage configurations, and flexible networking options. These capabilities make virtual machines particularly well suited for a wide range of scenarios, from development and testing to full production deployments. One of the most significant advantages of Azure Virtual Machines is the ability to scale resources dynamically based on demand. Organizations can quickly provision new instances when needed and scale down during periods of lower usage, ensuring cost-effective resource utilization. This pay-for-what-you-use model represents a fundamental shift from traditional infrastructure investments. The shared responsibility model clearly delineates which aspects of the service are managed by Microsoft and which remain under customer control. While Microsoft maintains responsibility for the physical infrastructure, including hardware maintenance, network connectivity, and data center operations, customers retain control over applications, data, operating systems, and related configurations. This division of responsibilities enables organizations to focus on their core business applications while leveraging Microsoft's expertise in infrastructure management. This arrangement differs significantly from both traditional on-premises deployments, where organizations manage everything, and platform as a service, PaaS, or software as a service, SaaS models, where Microsoft assumes greater responsibility for the technology stack. In the IaaS model, customers maintain the flexibility they need while offloading the complexities of physical infrastructure management to Microsoft. Azure's Infrastructure as a Service (IaaS) offering, particularly through virtual machines, enables organizations to implement powerful solutions across various scenarios. Let's explore 3 key implementation areas that demonstrate the versatility and value of IaaS. Test and development environments represent a prime use case for IaaS. Development teams can rapidly provision and deprovision environments as needed, significantly accelerating the application development lifecycle. This agility is particularly valuable in modern DevOps practices, where quick iteration and testing are essential. The ability to scale these environments up or down on demand ensures cost-effective resource utilization while maintaining development velocity. Website hosting through IaaS offers compelling advantages over traditional hosting solutions. Organizations can achieve significant cost savings while gaining greater control over their hosting infrastructure. The flexibility to adjust resources based on traffic patterns ensures optimal performance during peak periods while minimizing costs during quieter times. This approach is particularly beneficial for websites with varying traffic patterns or those requiring specific customizations not available in standard hosting platforms. Storage, backup, and recovery capabilities in IaaS address critical business continuity needs. Organizations can avoid substantial upfront storage investments while maintaining complete control over their data management strategies. The platform simplifies compliance with legal and regulatory requirements through built-in tools and features. The ability to scale storage resources dynamically accommodates both predictable growth and unexpected spikes in data volume, ensuring consistent performance without over-provisioning. Moving beyond basic infrastructure needs, IaaS enables several advanced computing scenarios that demonstrate its true potential. Let's examine 3 sophisticated use cases that showcase the power of virtual machines in Azure. High-performance computing (HPC) represents a transformative application of IaaS. Organizations can leverage virtual machines to create powerful computing clusters capable of solving complex problems involving millions of calculations. This capability proves invaluable in scenarios such as earthquake simulations, protein folding analysis, weather prediction, and financial modeling. The ability to scale these resources on demand makes HPC accessible to organizations that previously couldn't justify the investment in dedicated supercomputing infrastructure. Big data analysis benefits significantly from the flexible computing resources provided by IaaS. Organizations can process massive datasets to uncover hidden patterns, trends, and associations without maintaining permanent high-performance infrastructure. This approach is particularly cost-effective for periodic or project-based analysis, where computing needs fluctuate. The ability to quickly provision and configure specialized virtual machines optimized for data processing ensures efficient resource utilization. Extended data center capabilities through IaaS offer a practical solution for organizations looking to expand their existing infrastructure. Rather than investing in physical hardware and facility space, organizations can seamlessly extend their data center into Azure. This hybrid approach provides additional capacity while maintaining integration with existing systems. The ability to connect physical and cloud networks creates a unified computing environment that combines the benefits of both worlds. This flexibility in implementation scenarios demonstrates why IaaS and virtual machines have become fundamental building blocks for modern IT infrastructure, enabling organizations to adapt and scale their computing resources according to their specific needs and circumstances. When planning an Azure virtual machine deployment, a systematic approach ensures optimal configuration and performance. The planning process involves several critical decisions that will impact the VM's functionality, accessibility, and cost-effectiveness. Network configuration serves as the foundation of your VM architecture. Azure Virtual Networks provide private connectivity between VMs and other Azure services within the same network. Consider your current network topology and future growth requirements when designing your virtual network structure. The VM naming strategy should follow your organization's naming conventions while meeting Azure's requirements. A well-planned naming scheme helps with resource organization and management, particularly in environments with multiple VMs. Location selection impacts both performance and cost. Choose a region that balances proximity to end users with compliance requirements and pricing considerations. Remember that certain features may only be available in specific regions. Size determination involves matching VM resources to workload requirements. Azure offers a wide range of VM sizes optimized for different scenarios, from basic web servers to high-performance computing. Select a size that provides adequate resources while maintaining cost efficiency. Cost analysis forms a crucial part of VM planning. Review the pricing model for your selected VM size and estimate additional costs for storage, networking, and other associated services. Consider reserved instances for long-term deployments to optimize costs. Storage planning involves selecting the appropriate type and amount of storage for your VM. Azure offers various storage options, including standard and premium SSDs, with different performance characteristics and price points. Consider both the operating system disk and any additional data disks required for your workload. Operating system selection should align with your application requirements and team expertise. Azure supports both Windows and Linux distributions, each with different licensing and maintenance implications. Consider factors such as support requirements, compatibility with your applications, and existing team skills when making this decision. The network configuration deserves special attention as it's fundamental to your VM's connectivity and security. Virtual networks in Azure provide isolated and highly secure environments for your VMs. Consider these key aspects. Private connectivity ensures secure communication between resources in the same virtual network. External access can be carefully controlled through network security groups. Hybrid connectivity options enable integration with on-premises networks. Subnet planning should accommodate both current needs and future growth. Remember that while most VM settings can be modified after deployment, network configurations are more permanent. Take extra time during the planning phase to ensure your network design meets both current requirements and future needs. Establishing effective naming conventions for Azure virtual machines is crucial for long-term manageability and organization. The name you choose serves both as the computer name within the operating system and as an Azure resource identifier, making it a critical element of your infrastructure. The technical constraints vary by operating system. Windows VMs are limited to 15 characters, while Linux VMs can use up to 64 characters. Within these constraints, your naming convention should incorporate several key elements to create meaningful, consistent identifiers. A well-structured VM name typically includes environment identifier, dev, prod, QA, to clearly indicate the machine's purpose. Location code, UWJNE, to specify the deployment region, instance number for multiple similar machines. Service or product identifier to indicate the VM's role. Role designation to specify the machine's function. Consider the example devaske webvm01. This name efficiently communicates that it's a development environment, dev, in US South Central, USC, functioning as a web server, web, and is the first instance, your one, of this configuration. This structured approach ensures that anyone in your organization can quickly understand the VM's purpose and context just by looking at its name. The naming convention should be established early in your cloud adoption journey, as changing VM names after deployment isn't a trivial task. Consistency in naming becomes increasingly important as your infrastructure grows, helping with automation, reporting, and general resource management. Selecting the appropriate location for your Azure virtual machines involves balancing multiple factors that can significantly impact performance, compliance, and cost. Azure's global infrastructure of data centers grouped into geographic regions provides flexibility in choosing where to deploy your VMs. Performance considerations often drive location selection. Placing VMs closer to your users reduces latency and improves application responsiveness. This proximity factor becomes particularly important for applications sensitive to network delays or those serving users in specific geographic areas. Compliance and regulatory requirements can restrict your location options. Many organizations must adhere to data residency requirements that mandate keeping data within specific geographic boundaries. Different regions may also have varying compliance certifications, affecting industries with strict regulatory frameworks. The availability of specific VM configurations varies by region. Not all hardware types or VM sizes are available in every location, and newer features often roll out to regions gradually. This variability means you should verify that your required configuration is available in your preferred region before making a final decision. Cost considerations play a crucial role in location selection. Azure's pricing varies between regions, sometimes significantly. When evaluating locations that meet your technical and compliance requirements, compare pricing across eligible regions to optimize costs. Consider both the direct VM costs and related expenses like data transfer and storage. Remember that location selection impacts more than just the VM itself. It affects your entire solution's architecture, including network latency between components, data transfer costs between regions, availability of related services, disaster recovery options, integration with existing systems. Take time to evaluate these factors carefully, as changing a VM's region after deployment typically requires recreating the VM in the new location. Selecting the appropriate size for your Azure virtual machine is a critical decision that directly impacts both performance and cost. The selection process should begin with a thorough analysis of your workload requirements, as different workloads demand different combinations of computing resources. Azure Managed Disks simplify storage management by handling the complexities of storage account creation and management behind the scenes. This managed service approach offers several advantages. Automatic storage management removes the burden of manually configuring and maintaining storage accounts. Performance tier selection, standard or premium, allows you to match storage performance to workload requirements. Dynamic scaling capabilities enable you to adjust storage resources without worrying about the underlying infrastructure. Simplified administration reduces operational overhead. When sizing your VM, consider these key factors. CPU requirements for your applications. Memory needs for optimal performance. Storage throughput and IOPS requirements. Network performance expectations. The ability to scale these components independently provides flexibility in resource allocation and cost management. For example, you can increase storage capacity without changing the VM's compute resources, or upgrade compute capacity without modifying storage configurations. Azure's VM pricing model separates compute and storage costs, providing transparency and flexibility in resource management. This separation allows for independent scaling and precise cost control based on your specific needs. Compute costs are calculated on a per-minute basis, though prices are listed hourly. Key aspects of compute pricing include consumption-based, option, pay-as-you-go pricing with per-minute billing, no long-term commitment required, ability to start-stop VMs as needed, ideal for development, testing, and variable workloads. Reserved virtual machine instances. Significant cost savings, up to 72%, with 1 or 3 year commitments. Predictable budgeting for steady-state workloads. Flexibility to exchange or return instances with a fee. Best suited for applications with consistent long-term usage. Storage costs remain independent of VM state and are charged continuously for any allocated storage. Important considerations for storage pricing. Costs persist even when VMs are deallocated. Different pricing for standard and premium tiers. Separate billing for additional features like snapshots or replication. Performance tier selection impacts overall costs. When selecting between pricing options, consider workload predictability, budget constraints, performance requirements, operational flexibility needs. This pricing structure enables organizations to optimize costs by matching payment models to usage patterns while maintaining the ability to scale resources independently as needed. Azure provides a comprehensive range of operating system options for virtual machines, accommodating diverse workload requirements while simplifying licensing management. The platform's approach to operating systems combines flexibility with convenience, offering multiple paths to deploying your preferred OS environment. Base operating system images come with several advantages. Windows and Linux distributions are readily available. Operating system licensing costs are bundled into the VM pricing. Regular updates and security patches are provided. Official support from both Microsoft and OS vendors. The Azure Marketplace expands these options significantly, offering pre-configured solutions that include both the operating system and popular software stacks. This approach provides several benefits. Reduced setup and configuration time. Tested and optimized configurations. Integrated software solutions. Regular updates and security patches. For organizations with specific needs, Azure supports custom image deployment. This flexibility allows you to upload your own disk images, maintain consistent configurations across deployments, Implement specialized software requirements. Ensure standardization across your infrastructure. Remember that Azure exclusively supports 64-bit operating systems, ensuring optimal performance and compatibility with modern applications and services. The Azure Marketplace represents a significant enhancement to the basic VM deployment process, offering pre-configured solution stacks that combine operating systems with popular software applications. This integration streamlines the deployment process and reduces the complexity of setting up complex environments. Consider the example of a LAMP stack deployment. Linux provides the operating system foundation. Apache serves as the web server platform. MySQL handles database responsibilities. PHP enables dynamic web application functionality instead of manually installing and configuring each component, which can be time-consuming and error-prone. The Marketplace allows you to deploy the entire stack as a single unit. This approach offers several advantages. Significantly reduced deployment time. Consistent configurations across deployments. Pre-tested component compatibility. Integrated security updates. Beyond basic stacks, the Marketplace offers a wide range of solutions. Content management systems, like WordPress, development environments and frameworks, security and monitoring tools, enterprise applications, data analytics platforms. When selecting Marketplace images, consider licensing costs and terms, update and maintenance requirements, performance optimization needs, support options and availability. This ecosystem of pre-configured solutions makes it possible to rapidly deploy complex environments while maintaining professional standards and best practices. Azure virtual machines utilize a structured approach to storage through virtual hard disks, VHDs, providing a familiar yet virtualized storage environment. Each VM is configured with multiple disk types, each serving specific purposes in the overall storage architecture. The operating system disk serves as the primary storage location for the VM's OS and system files. This disk is always present and is configured as a SATA drive, appearing as the C drive in Windows environments. It contains the pre-installed operating system selected during VM creation and maintains persistent storage across VM operations. The temporary disk provides a workspace for short-term storage needs, but comes with important limitations. In Windows, it appears as the D drive and hosts the page file, .cas. In Linux, it's typically mounted as dev.sdb and managed by the Azure Linux agent. Data persistence is not guaranteed during maintenance events. Content may be lost during VM redeployments or host migrations. Critical considerations for VM storage management. Never store important data on temporary disks. Two-plan storage configuration based on workload requirements. Understand the persistence characteristics of each disk type. 4. Consider performance requirements when selecting storage options. Storage configuration in Azure VMs follows platform-specific patterns that administrators need to understand for effective management. The configuration varies between Windows and Linux environments, though the underlying principles remain consistent. Windows storage configuration. The OS disk is mapped as C drive and contains system files. Temporary storage is assigned to D drive by default. The page file .cas is automatically placed on the temporary disk. Additional data disks are assigned subsequent drive letters, E onwards, Linux storage configuration. The OS disk appears as dev.sda. Temporary storage is configured as dev.sdb. The Azure Linux agent handles temporary disk formatting. The temporary disk is typically mounted at .mnt. Storage best practices. Use OS disks primarily for system files too. Reserve temporary storage for non-critical, transient data. 3. Configure data disks for application data. Storage 4. Implement appropriate backup strategies for persistent storage. 5. Monitor storage performance and usage patterns. C. Plan for scaling storage capacity as needed. Understanding these configurations and their implications is crucial for proper application deployment, data persistence management, performance optimization, cost control, disaster recovery planning. Data disks in Azure virtual machines provide dedicated storage for application data, offering flexibility and scalability beyond the operating system disk. These SCSI drives can be configured with custom drive letters and serve as the primary storage solution for your application's persistent data needs. Key aspects of data disk implementation: capacity and limits. Storage capacity up to 256 TB per virtual machine. Number of attachable disks depends on VM size. Performance scales with number of disks. Custom drive letter assignment for easy management throughout performance capabilities. Up to 80,000 IOPS per virtual machine. Throughput reaching 2,000 MBs. Low latency for read operations. Performance varies by storage type. Selected 3. Manage disk options. Ultra SSD for extreme performance requirements. Premium SSD for production workloads. Standard SSD for balanced cost and performance. Standard HDD for cost-effective storage. These capabilities enable organizations to build storage solutions that match their specific workload requirements while maintaining flexibility for future growth and changes in demand. Optimizing storage for Azure virtual machines involves careful consideration of various factors to achieve the best balance of performance, cost, and reliability. Azure offers several strategies and options for maximizing storage efficiency. Premium storage considerations. Ideal for I/O-intensive workloads. SSD-based storage for consistent performance. Low latency for critical applications. Ability to migrate existing disks. Cost premium justified by performance gains. Multiple storage disk strategy. Distribute workload across multiple disks. Aggregate performance benefits. Enhanced reliability through separation. Flexible capacity management, improve backup and recovery options, manage disks benefits, simplified storage management, automatic scaling and maintenance, enhanced reliability through built-in redundancy, reduced administrative overhead, required for single-instance VM SLAP performance optimization, migrate high IOPS workloads to premium storage. 2. Use standard storage for lower priority workloads. Monitor and adjust based on usage patterns. 4. Consider cost-performance trade-offs. 5. Plan for future scaling requirements. Remember that storage choices significantly impact both application performance and operational costs. Regular assessment of storage needs and performance metrics helps ensure optimal configuration for your specific use case. Creating a virtual machine in the Azure portal involves a systematic process through multiple configuration tabs, each focusing on specific aspects of the VM deployment. Understanding these configuration options is crucial for proper VM setup. The Basics tab serves as the starting point, where you define fundamental settings. Project details including subscription and resource group, administrator account credentials, initial security settings through inbound port rules, basic VM specifications and image selection. Moving to the Disks tab, you'll configure storage options, OS disk type selection, standard or premium, data disk configuration and attachment, disk encryption settings, performance tier selection. The Networking tab handles connectivity configuration, virtual network creation or selection, subnet configuration, public IP settings, network security group rules, load balancing options. Management settings provide operational control. Boot diagnostics configuration. Auto shutdown schedules. Backup policy assignment. System assigned managed identity options. Selecting the appropriate VM image is a crucial first step in the VM creation process. Azure provides a comprehensive range of operating system images and marketplace solutions to meet diverse workload requirements. Operating system options, Windows images, server editions for various workloads. Client platforms for development and testing. Specialized versions for specific applications. Regular updates and security patches, Linux images. Popular distributions, Ubuntu, Red Hat, SUSE. Server optimized configurations, development and production environments, community and enterprise support options. Azure Marketplace extends these options with pre-configured application stacks, industry-specific solutions, third-party applications and services, optimized configurations, advanced configuration considerations, automatic OS updates and patch management. 2. Custom image requirements, license management. 4. Regional availability. Performance optimization needs. The portal's guided configuration process ensures all necessary components are properly configured while maintaining flexibility for customization based on specific requirements. Azure provides multiple secure methods for connecting to virtual machines, each designed to meet different operational needs and security requirements. Understanding these connection options is crucial for effective VM management and security. Connection methods. Overview, Azure Bastion. Fully managed path solution for secure VM access. SSL encrypted connections for both RDP and SSH. No requirement for public IP addresses. Direct integration with Azure Portal. Zero client software requirements. Remote desktop protocol, RDP. Primary method for Windows VM connections. Provides full graphical user interface. Configurable port settings. Downloadable RDP file for connection. Support for advanced features like clipboard sharing. SSH connections. Standard method for Linux VM access. Command line interface. Key-based authentication support. Secure encrypted communications. Integration with standard SSH tools. Cloud Shell. Browser-based command line interface. Pre-configured authentication. Integrated Azure tools. Platform-independent access. Azure Bastion and RDP connections represent two primary approaches to accessing Windows virtual machines, each with distinct characteristics and security implications. Azure Bastion Service. Security features. SSL encrypted connections. No exposure of RDP SSH ports to Internet. Virtual network integration. Native Azure AD authentication. Automated security patching. Operational benefits. Zero client requirements. Direct portal access. Simplified management. Consistent access method. Cross-platform compatibility RDP connection process. One IP address. Configuration. Specify target VM IP. Configure connection port. Generate RDP connection file 2. Authentication. Credential validation. Multi-factor authentication support. Session encryption 3. Session management. GUI access resource sharing options. Session persistence settings. Performance tuning capabilities. Best practices. 1. Use Azure Bastion when possible. 2. Implement proper access controls. 3. Monitor connection attempts. 4. Regular security reviews. 5. Maintain current patches. SSH, Secure Shell, provides a secure method for connecting to Linux-based virtual machines in Azure. This encrypted connection protocol ensures secure authentication and communication, making it the standard choice for Linux VM management. Key components of SSH. Public key infrastructure. Public key placed on VM during setup. Private key retained locally. Asymmetric encryption for security. Key pair reusability across multiple VMs. Connection process. 1. Authentication initiation. Key pair. Verification. Encrypted session establishment. 4. Secure command execution management benefits. Single key pair for multiple resources. Simplified access management. Integration with existing tools. Cross-platform compatibility. Automated script support. Securing SSH connections to Azure Linux VMs requires careful attention to key management and security practices. The asymmetric key pair system provides robust security when properly implemented and maintained. Key security considerations: private key protection, store in secure location. Restrict access permissions, never share or transmit, maintain secure backups. Regular rotation schedule, public key management, can be shared safely. Deploy across multiple VMs. Update as needed. Monitor distribution best practices. Implement strong key encryption. 2. Use key passphrase protection. Regular security audits. 4. Monitor access attempts. 5. Maintain access logs. 6. Follow organizational policies, operational guidelines. Restrict root SSH access. Use custom ports when necessary. Implement connection timeouts. Enable only required authentication methods. Regular security updates. Access control monitoring. Remember, the security of your SSH connections depends primarily on protecting your private key. While public keys can be freely distributed, private keys must be treated as sensitive security credentials and protected accordingly. Time for knowledge. Check question 1. Compute-optimized virtual machine explanation. Compute-optimized virtual machines are specifically designed for network appliances and other compute-intensive workloads. These VMs have a high CPU-to-memory ratio, making them ideal for network appliances. Medium traffic web servers. Batch processes. Application servers, memory-optimized VMs are better suited for database workloads, while storage-optimized VMs are designed for high disk throughput scenarios. Question 2. Configure Azure Bastion. Explanation. Azure Bastion is the ideal solution when security policies prohibit exposing SSH ports to external connections because it provides secure SSH connectivity without exposing public endpoints. Connections are made directly through the Azure portal. It uses SSL for secure connectivity. No public IP addresses are required on the VMs. It eliminates the need for managing jump servers. Question 3. Outbound requests are allowed. Inbound traffic is allowed only from within the virtual network. Explanation. By default, Azure virtual machines are configured with the following network security settings. Outbound traffic is allowed to any destination. Inbound traffic is restricted to resources within the same virtual network. This configuration provides a secure starting point that can be customized as needed. Additional inbound rules can be added through network security groups. This default configuration balances security with usability by allowing VMs to access necessary resources and updates, protecting VMs from unauthorized external access, enabling communication between resources in the same virtual network, providing a foundation for more specific security rules. Let's explore Azure maintenance planning, a crucial aspect of cloud infrastructure management that directly impacts your system's reliability and performance. As Azure administrators, we need to understand and prepare for various types of maintenance scenarios that can affect our virtual machines. Let's begin with unplanned hardware maintenance. This scenario occurs when Azure's sophisticated monitoring systems predict an imminent hardware failure in the physical infrastructure. Rather than waiting for an actual failure, Azure proactively addresses these situations using live migration technology. This technology transfers your virtual machines from potentially failing hardware to healthy physical machines. While this process primarily occurs in the background, you might notice a slight performance impact before or after the migration. However, the key advantage is that your virtual machines remain operational throughout the process. Moving on to unexpected downtime, which presents a more challenging scenario. This occurs when there's a sudden failure in the physical infrastructure supporting your virtual machines. These failures can range from local network issues to disk failures or even broader rack-level problems. Azure's response to these situations is automatic and decisive. The platform immediately initiates a migration process to move your virtual machine to healthy hardware within the same data center. It's important to note that this healing procedure does involve some downtime as your virtual machine needs to reboot. Additionally, there's a possibility of losing data stored on temporary drives, which underscores the importance of proper data management practices. The third type of maintenance is planned maintenance, which Microsoft conducts periodically to enhance the Azure platform's reliability, performance, and security. These updates are essential for maintaining the robust infrastructure that supports your cloud operations. The good news is that most of these planned maintenance activities are designed to occur without any impact on your virtual machines or cloud services. Microsoft has invested significantly in technologies that minimize disruption during these necessary updates. A crucial point to remember is that while Microsoft manages the platform infrastructure, you retain complete control over your virtual machine's operating system and application updates. This arrangement gives you the flexibility to manage updates according to your organization's needs and schedule. You can implement your own update policies, conduct testing, and ensure updates align with your business requirements. To effectively manage these maintenance scenarios, consider implementing these best practices. Regularly back up your data and store it independently from your virtual machines. Implement appropriate redundancy measures, such as using availability sets or zones. Document and regularly test your disaster recovery procedures. Monitor your virtual machine's performance metrics to detect potential issues early. Keep your team informed about Azure's maintenance notifications and schedule. By understanding these maintenance types and implementing appropriate strategies, you can maintain high availability while minimizing the impact of both planned and unplanned maintenance events. Remember, successful Azure administration isn't just about reacting to maintenance events. It's about preparing for them proactively. Diving into Azure availability sets, a fundamental feature that helps ensure your applications remain available and resilient in the cloud. Let me walk you through this crucial concept and its implementation details. An availability set is essentially a logical grouping mechanism in Azure that plays a vital role in maintaining application reliability. Think of it as a strategic way to organize your virtual machines to protect against both hardware failures and planned maintenance events. When you place multiple virtual machines in an availability set, Azure ensures they're distributed across different physical infrastructure components, creating multiple layers of redundancy. Let's explore the key principles of availability sets. First and foremost, all virtual machines within an availability set should be identical in terms of their role and software configuration. This isn't just a recommendation, it's a fundamental design principle. These machines should perform the same functions and run the same software stack, effectively creating a redundant group of resources. Azure takes care of distributing these virtual machines across multiple physical servers, compute racks, storage units, and network switches. This distribution is automatic and ensures that if a hardware failure occurs, or when Azure needs to perform maintenance, only a subset of your virtual machines is affected. The result: your application continues to run and serve your customers, even during infrastructure-level events. A critical point to remember about availability sets is the timing of their configuration. You must decide whether to use an availability set when you first create a virtual machine. This isn't a setting you can easily change later. If you need to modify the availability set for a virtual machine, you'll need to delete and recreate that VM. This limitation emphasizes the importance of proper planning in your deployment strategy. The implementation of availability sets is flexible, offering multiple deployment options. You can create them through various methods: the Azure portal for those who prefer a graphical interface, Azure Resource Manager templates for infrastructure as code, or through scripting and API tools for automation scenarios. This flexibility allows you to choose the method that best fits your operational practices. Microsoft backs the reliability of availability sets with robust service level agreements, SLAs, for virtual machines. These SLAs provide concrete guarantees about the availability of your services, giving you confidence in your application's uptime. However, there's an important caveat to keep in mind. Availability sets protect against infrastructure-level failures, but they don't provide comprehensive protection against all types of failures. They won't shield your applications from operating system crashes or application-specific issues. For complete protection, you need to implement additional disaster recovery and backups. When designing reliable cloud solutions in Azure, availability sets play a crucial role in your architecture. Today, I'll walk you through the essential considerations that will help you implement availability sets effectively and maximize their benefits for your applications. Let's start with redundancy, which forms the foundation of high availability in Azure. When implementing availability sets, it's crucial to deploy multiple virtual machines within each set. This approach isn't just about having backup machines. It's about creating a resilient infrastructure that can maintain service continuity, even when individual components fail. Think of it as having multiple engines on an aircraft. If one experiences issues, the others keep you safely in the air. Application tier separation is our next critical consideration. In a multi-tier application architecture, each tier should reside in its own dedicated availability set. For instance, your web servers should be in one availability set, your application servers in another, and your database servers in a third. This separation prevents a single point of failure from cascading through your entire application stack. It's like having separate backup generators for different sections of a hospital. If one fails, critical operations can continue in other areas. Load balancing is where we start to optimize performance alongside availability. Azure Load Balancer works hand in hand with availability sets to distribute incoming traffic across your virtual machines. When you create a load-balanced availability set, you're not just ensuring high availability, you're also implementing intelligent traffic routing that can improve response times and overall application performance. The load balancer continuously monitors the health of your instances and automatically directs traffic only to operational servers. Storage considerations are equally important, which is why Azure Managed Disks are recommended for virtual machines in availability sets. Managed disks simplify your storage management while providing enhanced reliability. They automatically handle storage allocation and scaling, ensuring that your storage infrastructure is as resilient as your compute resources. Think of managed disks as your storage safety net, providing built-in redundancy and simplified management. Here are some practical tips for implementing these considerations. For redundancy, always deploy at least 2 VMs in each availability set. Consider your application's load when determining the number of instances. Plan for N+1 redundancy, where N is your minimum required instances for application tier separation. Map out your application tiers before creating availability. Sets document dependencies between tiers. Consider using naming conventions that reflect tier separation for load balancing. Configure health probes to monitor instance availability, Set appropriate load balancing rules based on your application's needs. Consider using internal load balancers for back-end tiers for managed disks. Choose the appropriate disk performance tier for your workload. Plan your storage capacity requirements. Consider using premium SSD managed disks for production workloads. When implementing these considerations, remember that they work together as part of a comprehensive availability strategy. The real power comes from their combination. Redundancy ensures service continuity. Tier separation prevents cascade failures. Load balancing optimizes performance. And managed disks provide reliable storage infrastructure. Let's explore two fundamental concepts in Azure Virtual Machine Availability Sets: update domains and fault domains. These components work together to create a comprehensive high-availability strategy for your cloud infrastructure. Update domains are Azure's way of managing planned maintenance and updates across your virtual machine fleet. Think of update domains as groups of virtual machines that undergo maintenance together. When Azure needs to perform platform updates, it does so one update domain at a time, ensuring that machines in other update domains remain operational and continue serving your applications. By default, Azure provides 5 update domains, but you can configure up to 20 for more granular control over the update process. This flexibility allows you to fine-tune how your applications handle planned maintenance. Imagine you're updating a building's electrical system. You wouldn't want to shut down power to all floors simultaneously. Similarly, update domains allow Azure to perform maintenance while keeping your services running. Moving on to fault domains, these represent physical units of failure in the Azure infrastructure. A fault domain essentially maps to physical hardware infrastructure. Think of it as a group of virtual machines that share common physical hardware components. They might be on the same rack, using the same power source, or connected to the same network switch. The beauty of fault domains lies in their role in hardware failure protection. Azure automatically distributes virtual machines across fault domains when you place them in an availability set. This distribution ensures that if a hardware failure occurs, whether it's a power issue, network problem, or hardware malfunction, only the virtual machines in that particular fault domain are affected. Let me illustrate this with a practical example. Imagine you have a web application with 4 virtual machines, 2 web servers and 2 SQL servers. Here's how you might structure them. Web tier. Web VM1 in fault domain. 1 Web VM2 in fault domain 2. Both part of the Web Availability Set database. Tier SQL VM1 in fault domain 1. SQL VM2 in fault domain. 2 both part of the SQL availability set. This configuration provides multiple layers of protection. If hardware fails in fault domain 1, you still have operational servers in fault domain 2. When Azure performs updates, it processes one update domain at a time. Your application remains available through both planned and unplanned events. Here are some best practices for working with update and fault domains. For update domains, plan your application architecture to handle one update domain being offline. Consider using more than the default 5 update domains for greater update granularity. Test your application's behavior during update domain rotations. For fault domains, always spread critical application components across multiple fault domains. Keep related services in the same availability set but different fault domains. Document your fault domain architecture for disaster recovery planning. The real power of these domains comes from their interaction. Each virtual machine in an availability set gets placed in both an update domain and a fault domain, creating a matrix of protection. This dual domain approach means your applications are resilient to both planned maintenance, handled by update domains, and hardware failures managed by fault domains. Azure Availability Zones, a sophisticated high-availability offering that provides robust protection against data center failures. Let me walk you through this crucial feature. and explain how it can enhance your cloud infrastructure's resilience. Availability zones represent a significant evolution in Azure's high availability architecture. Each zone is essentially a unique physical location within an Azure region, equipped with its own independent infrastructure. Think of these zones as self-contained data centers, each with dedicated power supplies, cooling systems, and networking infrastructure. This independence is crucial. It means that if one zone experiences issues, the others remain fully operational. Microsoft has implemented a minimum of 3 separate zones in all enabled regions. This 3-zone minimum isn't arbitrary. It's designed to provide optimal redundancy while maintaining practical operational efficiency. The physical separation between these zones is carefully planned to protect against localized failures while still maintaining the low latency benefits of being within the same region. Let's dive into how Azure services interact with availability zones through 2 distinct categories: zonal services and zone redundant services. Zonal services are those that are specifically pinned to a particular zone. These include Azure Virtual Machines, which you can deploy to a specific zone of your choice; Azure Managed Disks, which are automatically placed in the same zone as their associated VM; standard IP addresses, which can be assigned to specific zonal resources. Zone redundant services, on the other hand, operate differently. These services automatically replicate across zones. Azure Storage with Zone Redundant Storage, ZRS, automatically replicates your data across 3 zones. Azure SQL Database can be configured for zone redundancy, maintaining synchronized copies across zones. Here's a practical example of how you might implement availability zones in your architecture. Imagine you're running a critical web application. You could deploy web server VMs across 3 zones. Use zone redundant storage for your application. Data implement a zone redundant SQL database for your backend. Configure a zone redundant load balancer to distribute traffic. This configuration provides multiple layers of protection. If a zone fails, your application continues running in the other zones. Your data remains accessible thanks to zone redundant storage. Database operations continue uninterrupted through zone redundancy. The load balancer automatically routes traffic to healthy zones. Some key considerations when implementing availability zones for application architecture: design your applications to be zone-aware. Implement proper load balancing across zones. Consider data residency and replication requirements. For business continuity, combine availability zones with region pairs for maximum protection. Plan for zone failure in your disaster recovery scenarios. Test your application's behavior during zone failures. For cost management, balance redundancy requirements with cost implications. Consider bandwidth costs between zones. Plan capacity across zones efficiently. A particularly powerful strategy is to combine availability zones with Azure region pairs. This approach provides protection against both data center failures through zones and regional disasters through region pairs. For instance, you might have primary deployment spread across 3 zones in your main region, secondary deployment in a paired region, also using zones' automated failover procedures between regions. The real strength of availability zones lies in their ability to provide high availability without sacrificing performance. Since zones are within the same region, you maintain low latency while gaining significant failure protection. This makes them ideal for applications that require both high availability and consistent performance. Let's explore the 2 fundamental approaches to scaling in Azure: vertical scaling and horizontal scaling. Understanding these approaches is crucial for building robust, scalable applications in the cloud. Let me guide you through their characteristics, advantages, and key considerations. Let's start with vertical scaling, often referred to as scaling up and down. Think of vertical scaling like upgrading your personal computer. You're essentially making a single machine more powerful by adding more CPU, memory, or other resources. In Azure, this means changing your virtual machine size to match your workload requirements. Vertical scaling offers several distinct advantages in specific scenarios. For instance, if you're running a database server that needs more processing power but isn't designed for distributed operations, vertical scaling might be your best option. It's also particularly useful for cost optimization. Imagine running a development environment that's only heavily used during weekdays. You could scale down the VM size during weekends to reduce costs and scale up again when developers return to work. However, vertical scaling comes with important limitations. There's an upper boundary to how much you can scale up, determined by the maximum VM size available in your region. Additionally, vertical scaling typically requires a VM restart, which means your application will experience some downtime during the scaling operation. Now let's explore horizontal scaling, or scaling out and in. Unlike vertical scaling, which makes individual machines more powerful, horizontal scaling adds or removes machines from your environment. Think of it like adding more workers to handle increased workload. Instead of making one worker stronger, you're bringing in additional team members. Horizontal scaling shines in several scenarios. When you need to handle unpredictable workload spikes for applications designed with distributed architecture, when you need to maintain high availability during scaling operations, for workloads that can be easily parallelized. The flexibility of horizontal scaling is one of its greatest strengths. You can potentially scale to thousands of instances, limited mainly by your subscription limits and budget rather than technical constraints. This makes it particularly well suited for cloud-native applications that need to handle variable loads. A critical aspect of both scaling approaches is re-provisioning, the process of replacing existing VMs with new ones. This is particularly important when updating to new VM images, moving to different hardware, implementing major configuration changes. Here are some best practices for implementing scaling strategies. For vertical scaling, schedule scaling operations during maintenance windows. Ensure your application can handle the restart process. Document VM size requirements for different workload levels. Consider using managed disks for faster scaling operations. For horizontal scaling, implement proper load balancing design applications to be stateless where possible. Plan for session persistence if required. Automate scaling operations based on metrics. When choosing between vertical and horizontal scaling, consider these factors. Response time requirements. Vertical scaling might be faster for immediate resource needs. Horizontal scaling provides better long-term flexibility cost considerations. Vertical scaling might be more cost-effective for predictable workloads. Horizontal scaling offers better cost optimization for variable loads. Application architecture. Some applications might only support vertical scaling. Modern cloud-native applications typically work better with horizontal scaling. Data management. Consider how your data layer handles scaling plan for data synchronization in horizontal scaling scenarios. Account for backup and recovery procedures. We're exploring Azure Virtual Machine Scale Sets, a powerful Azure compute resource that revolutionizes how we handle scalable workloads in the cloud. Let me walk you through this essential technology and its capabilities. Virtual machine scale sets represent a significant advancement in cloud infrastructure management. At its core, this technology allows you to deploy and manage a collection of identical virtual machines with true auto-scaling capabilities. Think of it as having a smart, self-adjusting pool of resources that expands and contracts based on your actual needs. The fundamental principle behind scale sets is simplicity through uniformity. When you implement a scale set, all virtual machines are created from the same base operating system image and configuration. This standardization is crucial because it eliminates the complexity typically associated with managing large numbers of virtual machines. Instead of dealing with individual configurations and network settings for each machine, you manage the scale set as a single entity. Let's explore the key capabilities that make scale sets particularly powerful. Load distribution. At Layer 4, scale sets integrate seamlessly with Azure Load Balancer for basic traffic distribution. For more sophisticated needs, they work with Azure Application Gateway, providing Layer 7 traffic distribution and SSL termination. This integration ensures your application remains responsive even as instance counts change. Fault tolerance. Scale sets automatically distribute VM instances across fault domains. If one instance experiences problems, others continue serving requests. This built-in redundancy ensures high availability for your applications. Auto-scaling capabilities. Scale sets can automatically adjust the number of instances based on demand. You can define rules based on metrics like CPU usage, memory consumption, or network traffic. Both scheduled and metric-based scaling rules can be implemented. Manual scaling remains available when needed. Here's a practical example of how scale sets work in production. During peak hours, the scale set might run 20 instances to handle high traffic. During quiet periods, it might scale down to 5 instances to optimize costs all. Scaling operations happen automatically based on your defined rules. Load balancing adjusts automatically as instances are added or removed. Scale sets are particularly well suited for several scenarios. Large-scale services, big data processing applications, containerized workloads, compute-intensive tasks, web applications with variable traffic patterns, implementation considerations, capacity planning. Standard deployments support up to 1,000 VM instances. Custom image deployments are limited to 600 instances. Plan your capacity needs accordingly. Image management. Use standardized images for consistency. Maintain image versions for updates. Consider using custom images for specialized needs. Monitoring and maintenance. Implement proper monitoring to track scaling events. Set up alerts for unusual scaling patterns. Regular maintenance windows for image updates. Best practices. Image configuration. Keep base images minimal and consistent. Use automation for post-deployment configuration. Maintain proper version control for images. Scaling rules. Set appropriate thresholds for scaling triggers. Implement cool-down periods to prevent oscillation. Consider business hours in scheduled scaling. Application design. Design applications to be stateless where possible. Implement proper session management. Plan for instance recycling. Cost management. Set maximum instance limits to control costs. Monitor scaling patterns for optimization. Use appropriate VM sizes for your workload. Let me guide you through the process of creating Azure Virtual Machine scale sets in the Azure portal. Understanding these configuration options is crucial for setting up a scale set that meets your specific requirements. Let's start with the fundamental decisions you'll need to make when creating a scale set. The first crucial choice is the orchestration mode, which determines how your scale set manages virtual machines. You have two options. Uniform orchestration mode defines a single VM model that Azure uses as a template. Creates identical instances based on this model, ideal for predictable, homogeneous workloads. Simplifies management and scaling operations. Flexible orchestration mode allows manual creation and addition of VMs. Supports different configurations within the same scale. Set provides more granular control over individual instances. Better suited for heterogeneous workloads. Moving on to image selection. This is where you choose the foundation for your virtual machines. The image you select determines the operating system and any pre-installed applications. Azure offers various options: platform images, standard Azure offerings, custom images, your own configured images, Azure Marketplace images, third-party solutions. The VM architecture choice between x64 and ARM64 depends on your specific workload requirements. x64 architecture. Traditional choice, widely supported, ARM64 architecture, emerging option, potentially better price performance for specific workloads. A significant cost optimization option is Azure Spot instances. Here's what to consider. offers substantial cost savings, up to 90% in some cases, works best for interruptible workloads, requires handling potential evictions, ideal for batch processing, testing, and development workloads. Let's explore the advanced configuration options that can significantly impact your scale set's behavior. Scaling beyond 100 instances. Default limit is 100 instances in a single placement group. Enabling beyond 100 allows up to 1,000 instances, affects availability characteristics, requires careful planning for large-scale deployments. Spreading algorithm configuration. Max spreading recommended. Provides optimal distribution, benefits resource redundancy, enhances fault tolerance, improves overall availability. Here are some best practices for configuring your scale set. Image selection. Choose images that are optimized for cloud deployment. Consider maintenance and update requirements. Test images thoroughly before deployment sizing. Strategy: select VM sizes based on workload requirements. Consider both current and future needs. Balance performance with cost scaling. Configuration. Set appropriate minimum and maximum instance counts. Configure scaling rules based on actual metrics. Include sufficient buffer for unexpected demands. Cost optimization. Evaluate Azure Spot instance compatibility. Use appropriate VM sizes. Implement proper auto-scaling rules. Implementation. Tips. For basic configuration, document your orchestration mode choice and reasoning. Maintain image version control plan for architecture-specific requirements. For advanced settings, consider availability requirements when choosing spreading options. Plan capacity requirements carefully. Document scaling decisions and thresholds for monitoring. Set up proper monitoring from the start. Configure appropriate alerts. Plan for regular performance reviews. Auto-scaling in Azure Virtual Machine Scale Sets, a powerful feature that automatically adjusts your application's capacity based on real-world demands. Let me guide you through this essential capability and its implementation considerations. Auto-scaling is fundamentally about achieving the perfect balance between performance and cost. Think of it as having an intelligent system that constantly monitors your application's needs and adjusts resources accordingly. This automation eliminates the need for manual intervention while ensuring optimal resource utilization. Let's break down the key aspects of auto-scaling. Automatic capacity adjustment. The system monitors predefined performance metrics. When thresholds are met, scaling rules automatically trigger. Adjustments happen in real time based on actual demand. Performance remains consistent during scaling operations. Scale-out scenarios. When application demand increases, several factors might trigger a scale-out event. Sustained high CPU usage across instances, increased memory pressure, growing request queue length, network bandwidth saturation. Here's how scale-out works in practice. Monitoring systems detect increased load. Autoscale rules evaluate the situation. New instances are automatically provisioned. Load balancer incorporates new instances. Application capacity increases smoothly. Scale-in benefits. During periods of lower demand, scale-in operations provide several advantages. Reduced operational costs, optimized resource utilization, automated instance reduction, maintained performance levels, scheduled event management. Auto-scaling can also handle predictable load patterns, business hours scaling rules, weekend adjustment patterns, holiday season capacity planning, maintenance window configurations. Let's look at some practical implementation strategies. Setting up auto-scale rules. Define clear scaling metrics. Set appropriate thresholds. Configure scaling increments. Establish monitoring periods. Performance thresholds. CPU utilization targets, typically 70-80%. Memory usage limits. Queue length triggers. Custom metric thresholds. Scale-out parameters. Instance increment size. Cooldown periods. Maximum instance limits, Trigger condition duration, scale. In safety, minimum instance counts. Gradual reduction rules, performance safeguards, buffer capacity, maintenance best practices for implementation. Metric selection. Choose metrics that truly reflect application. Health, consider multiple metrics for scaling decisions. Test metric thresholds thoroughly. Monitor metric patterns over time rule. Configuration. Start with conservative rules. Implement appropriate cooldown periods. Set reasonable minimum and maximum limits. Document rule rationale, operational considerations. Monitor scaling operations closely. Set up alerts for unusual patterns. Regular review and adjustment of rules plan for capacity limits. Cost optimization. Balance performance with instance counts. Implement scale-in rules. Let's walk through the process of configuring auto-scaling in Azure Virtual Machine Scale Sets. This configuration is crucial for establishing an efficient and cost-effective scaling strategy. Let me guide you through each important setting and its impact on your implementation. Let's start with the fundamental choice between scaling policies. You have two primary options. Manual scaling maintains a fixed number of instances suitable for predictable workloads, provides direct control over resource allocation, simpler to manage and predict costs. Custom auto-scale dynamically adjusts based on metrics, supports schedule-based scaling, adapts to changing workload patterns, optimizes resource utilization automatically. Once you've chosen custom auto-scale, you'll need to configure several critical parameters. Instance boundaries, minimum VM count, sets your baseline capacity. Maximum VM count, controls cost and resource limits. Default count, starting point for scaling operations. These boundaries create a safe operating range for your auto-scaling operations. Let's look at how to configure scale-out rules. Scale-out configuration. CPU threshold. Setting. Determines when to add instances, typically set between 70 or 80% should reflect application performance requirements. Consider buffer for sudden spikes duration window. Critical for stability, typically 5 to 10 minutes. Prevents reaction to brief spikes, allows metrics to stabilize instance increment. Number of VMs to add balance between responsiveness and stability. Consider application startup time. Factor in cost implications. For scale-in operations, you'll configure scale-in configuration. CPU threshold, lower than scale. Out threshold creates a buffer zone, prevents oscillation. Typically, 20-30% below scale-out instance decrement VMs to remove, usually smaller than scale-out increment. Gradual reduction preferred, maintains service stability. Scale-in policy, determines VM removal order, considers instance age, balances availability, protects critical instances, best practices for configuration. Threshold selection. Start conservative, monitor and adjust. Consider multiple metrics. Test thoroughly time. Windows. Match application patterns, account for startup time. Consider cooldown periods, allow for metric stabilization. Increment sizing. Start small. Match capacity needs. Consider cost impact balance with application requirements. Policy implementation. Document decisions. Regular review, monitor. Effectiveness adjust as needed. Implementation. Tips for scale-out. Set appropriate buffer zones. Consider lead time for new instances. Plan for peak demands, monitor scaling patterns. For scale, implement gradual reduction. Protect critical workloads. Consider session handling plan for data consistency. For monitoring, set up alerts, track scaling events. Monitor costs, review effectiveness. Let's go through each question and understand the correct answers and their explanations. Question 1. How can you ensure more virtual machines are deployed when the CPU is 75% consumed? Correct answer. Enable the autoscale option. Explanation. The autoscale option is the key to automatically deploying additional virtual machines based on CPU consumption thresholds. Here's why this is the correct solution. Autoscale automatically monitors resource utilization. It can be configured with specific CPU percentage triggers. When enabled, it automatically handles scaling without manual intervention. It maintains consistent performance by responding to demand. The other options are less effective because manually increasing the instance count doesn't provide automated response to CPU usage. Changing the CPU percentage to 50% without enabling autoscale won't trigger automatic deployment. Question 2. Which virtual machine scale sets feature can be configured to add more DevOps machines during peak production? Correct answer: schedule-based rules explanation. Schedule-based rules are ideal for handling predictable workload patterns like the DevOps team's scenario because they can be set for specific days and times, Thursday evening peaks. They handle regular patterns automatically. They can be configured for both scale-out and scale-in operations. They're perfect for known business cycles. This is better than the alternatives because regular autoscale might not anticipate the predictable peaks. Metric-based rules respond to current conditions rather than planning for known patterns. Question 3. What types of scaling can you use to increase the CPU capacity for your existing virtual machine scale sets instances? Correct answer: vertical scaling explanation. Vertical scaling is the correct choice for increasing CPU capacity of existing instances because it increases the resources, CPU, memory, of existing VMs. It modifies the size power of current instances rather than adding more. It's ideal when you want to enhance individual instance capability. The other options don't fit the requirement because horizontal scaling adds more instances rather than increasing capacity of existing ones. Load balancing distributes traffic but doesn't increase instance capacity. Key learning points. 1. Automation and monitoring. Autoscale provides automated resource management. Schedule-based rules handle predictable patterns. Different scaling types serve different needs. 2. Resource management. Vertical scaling increases individual instance power. Horizontal scaling adds more instances. Choose the right approach based on specific needs. 3. Implementation considerations. Configure appropriate thresholds for autoscaling. Plan for both peak and low usage periods. Consider cost implications of different scaling approaches. Let's explore the fundamental aspects of Azure App Service Plans and understand how they form the backbone of your web hosting infrastructure. App Service Plans serve as the foundation for your applications, defining both the capabilities and limitations of your hosting environment. Starting with the regional deployment, Azure offers you the flexibility to choose from multiple geographical locations worldwide. This choice is crucial for optimizing latency and ensuring compliance with data residency requirements. Whether you need your applications closer to your users in West US, Central India, or North Europe, the choice of region can significantly impact your application's performance and user experience. When it comes to virtual machine instances, you have precise control over both quantity and size. The number of VM instances directly affects your application's ability to handle concurrent requests and provides high availability. You can start small with a single instance and scale up as your needs grow. The size of these instances, ranging from small to large, determines the processing power, memory, and storage available to your applications. In terms of scaling capabilities, App Service Plans offer different options based on their pricing tier. In the free and shared tiers, applications share resources with other customers and have limited scaling capabilities. However, when you move to basic, standard, premium, or isolated tiers, you gain access to dedicated compute resources and advanced scaling features. For resource-intensive applications, it's crucial to understand how applications share resources within a plan. All applications within the same plan share the available resources, including CPU, memory, and network capacity. This sharing extends to development slots, diagnostic logs, and background tasks like web jobs. While this can be cost-effective, it requires careful capacity planning to prevent resource contention. Consider the practical implications of your plan choices. For instance, when running multiple applications in a single plan, you can achieve cost savings through resource sharing. However, this approach requires careful monitoring to ensure one application doesn't negatively impact others. In situations where an application requires dedicated resources or different geographical deployment, creating a separate plan might be the better choice. Advanced features become available as you move up the pricing tiers. The standard tier and above support auto-scaling, allowing your applications to automatically adjust to changing workloads. These tiers also provide additional capabilities like custom domains with SSL certificates, deployment slots for staging environments, and daily backups. Remember that an app service plan's configuration isn't set in stone. You can modify most settings, including scaling up to more powerful hardware or scaling out to more instances as your requirements evolve. Let's explore the Azure App Service Plan pricing tiers, which form a crucial part of your application hosting strategy. Understanding these tiers helps you make informed decisions about resource allocation and cost management. Starting at the entry level, we have the free and shared tiers. These are your development and testing workhorses, perfect for initial application development phases. Keep in mind that in these tiers, your applications share virtual machines with other customers' applications. While this keeps costs minimal, it comes with limitations. You're restricted to 1 GB of disk space, and you can host up to 10 apps in the shared tier. These tiers don't come with an SLA, so they're not suitable for production workloads. Moving up to the basic tier, we enter the realm of dedicated computing resources. This tier is ideal for applications with moderate traffic requirements. You get 10 GB of storage and can scale up to 3 instances. The basic tier introduces built-in load balancing, distributing traffic automatically across your instances. While it doesn't support auto-scaling, it provides a stable environment for applications that have predictable traffic patterns. The standard tier marks your entry into production-grade hosting. This is where things get interesting with auto-scaling capabilities, allowing your application to automatically adjust to traffic demands. You get 50 GB of storage and can scale up to 10 instances. Standard tier also introduces deployment slots, giving you 5 staging environments for testing changes before going live. This tier is perfect for businesses running production workloads that need reliable performance and scaling capabilities. For enhanced performance, the premium tier takes things up a notch. It offers DV2 series virtual machines with faster processors and SSD storage. You get a generous 250 GB of storage and can scale up to 30 instances. The memory-to-core ratio is doubled compared to the standard tier, providing better performance for memory-intensive applications. Premium V2, the upgraded version, offers even better performance metrics while maintaining all the advanced features of the standard tier. At the top of the hierarchy sits the isolated tier, designed for mission-critical workloads that require maximum security and performance. This tier provides a completely dedicated and isolated running environment in an Azure data center through App Service environment. With 1 TB of storage and the ability to scale up to 100 instances, more available upon request, it's built for enterprise-grade applications. The isolated network environment makes it perfect for applications that need to run within a virtual network or require high levels of security and isolation. When choosing a tier, consider not just your current needs but your future requirements as well. Factor in aspects like traffic patterns, security requirements, and the need for development or testing environments. Remember that while you can scale up to a higher tier as needed, some transitions, like moving to or from the isolated tier, require more planning and potential application modifications, Each tier builds upon the features of the previous one, adding capabilities that support more complex and demanding scenarios. From simple development environments to enterprise-grade solutions, Azure App Service Plans provide a clear progression path that can grow with your application's needs. The key is to align your choice with both your technical requirements and business objectives, ensuring you get the best value for your investment, while maintaining the performance and reliability your applications need. Let's explore the powerful scaling capabilities of Azure App Service, which provide you with the flexibility to adapt your application's resources to meet changing demands. Understanding these scaling options is crucial for maintaining optimal performance while managing costs effectively. Azure App Service offers two primary scaling approaches: scaling up, vertical scaling, and scaling out, horizontal scaling. Each method serves different purposes and can be implemented either manually or automatically through autoscale features. When we talk about scaling up, we're essentially upgrading your application's power by moving to a higher pricing tier or choosing a more powerful compute instance. This vertical scaling approach increases your CPU, memory, and disk space allocations. Think of it as upgrading from a compact car to a luxury vehicle. You're getting more power and features in the same package. As you scale up through different tiers, you unlock additional features like custom domains, SSL certificates, staging slots, and auto-scaling capabilities. On the horizontal front, scaling out multiplies your application's capacity by adding more virtual machine instances. Depending on your pricing tier, you can scale out to as many as 30 instances, with the isolated tier supporting up to 100 instances through app service environments. This approach is particularly effective for handling increased traffic loads and ensuring high availability. It's like adding more lanes to a highway rather than replacing it with a bigger road. The beauty of Azure's auto-scale feature lies in its ability to automatically adjust your instance count based on predefined rules and schedules. You can set conditions based on metrics like CPU usage, memory consumption, or request queue length. This automation ensures your application maintains performance during peak times while scaling back during quieter periods to optimize costs. One of the most compelling aspects of Azure App Service scaling is its seamless implementation. Whether you're scaling up or out, there's no need to modify your application code or redeploy your solution. Changes take effect within seconds, affecting all applications within your app service plan. This flexibility allows you to adapt quickly to changing requirements without disrupting your application's availability. Consider a practical scaling strategy. Start with a lower tier during development and testing phases, then scale up as you need additional features. For instance, begin with the free tier for initial development, move to shared when you need a custom domain, upgrade to basic for SSL support, and progress to standard when you require staging environments. This approach ensures you're only paying for the features you need when you need them. When implementing autoscale, think about your application's usage patterns. Set rules that anticipate traffic spikes during business hours or special events, and configure scale down. Let's explore Azure App Service Autoscale Configuration, a powerful feature that helps you maintain optimal application performance while managing costs effectively. Understanding how to properly configure autoscale settings is crucial for creating a responsive and cost-efficient application environment. At its core, autoscale configuration revolves around setting up intelligent rules that automatically adjust your application's resources based on demand. Think of it as having an automated system that monitors your application's pulse and adjusts its resources accordingly. To implement this effectively, you need to understand and configure several key components. First, let's talk about instance boundaries. You'll need to set both minimum and maximum instance counts. The minimum instance count acts as your safety net, ensuring your application always has enough resources to remain responsive, even during low traffic periods. The maximum instance count, on the other hand, serves as your cost control mechanism, preventing runaway scaling during unexpected traffic spikes. When setting these boundaries, ensure there's an adequate margin between them to allow for flexible scaling. Auto-scale rules come in two flavors: metric-based and time-based. Metric-based rules respond to performance indicators like CPU usage, memory consumption, or request queue length. For example, you might configure a rule to add an instance when CPU usage exceeds 70% for more than 10 minutes. Time-based rules, alternatively, allow you to anticipate and prepare for known traffic patterns. You could set up a rule to increase capacity every Monday morning, before your peak business hours begin. A crucial aspect of autoscale configuration is implementing complementary scale-out and scale-in rules. These rules work together like a thermostat in your home. Scale-out rules determine when to add resources, while scale-in rules specify when to remove them. Without proper scale-in rules, you might end up paying for unnecessary resources during low traffic periods. Conversely, without appropriate scale-out rules, your application might become unresponsive during high traffic periods. Metric statistics play a vital role in how your autoscale rules make decisions. When configuring metrics, you'll need to choose between different statistical methods: average, minimum, maximum, or total. Your choice depends on your application's nature and requirements. For instance, if you're concerned about brief spikes in CPU usage, you might want to use maximum values rather than averages. Don't overlook the importance of setting an appropriate default instance count. This count serves as your fallback position when metrics are unavailable or during system transitions. Choose a value that provides adequate performance while maintaining cost efficiency. Think of it as your application's neutral gear, ready to scale up or down as needed. Notifications are your window into the autoscale system's operation. Configure them to alert relevant team members when scaling events occur or when the system encounters issues. You can set up email notifications or webhook calls to integrate with your existing monitoring and alerting systems. This visibility helps you maintain awareness of your application's performance and resource utilization patterns. For optimal results, consider implementing a combination of rules that work together. For example, you might use metric-based rules for immediate response to load changes, complemented by time-based rules that prepare for known busy periods. This hybrid approach provides both reactive and proactive scaling capabilities. Remember to regularly review and adjust your autoscale settings based on real-world performance data and changing business requirements. Pay attention to patterns in your scaling history and adjust thresholds and rules accordingly. Are you scaling too frequently? Not frequently enough? Are your instance boundaries appropriate for your current traffic patterns? When implementing autoscale, start conservatively and gradually refine your settings. Begin with wider margins between scaling events to prevent oscillation, then tighten them as you understand your application's behavior better. Monitor the impact of your autoscale settings on both performance and cost, making adjustments to find the optimal balance for your specific needs. By carefully configuring these autoscale components, you create a self-adjusting system that maintains performance while optimizing resource utilization. The key is to think of autoscale not as a set-and-forget feature, but as a dynamic system that requires ongoing monitoring and refinement to deliver the best results for your application. Let's analyze each question and understand the correct answers with detailed explanations. Question 1. Which app service plan can you implement to support the production team's requirements? Answer: Premium. The Premium tier is the correct choice for the production team's requirements. Here's why. The production team needs 100 GB of disk storage, which exceeds the standard tier's 50 GB limit. Premium tier offers 250 GB of disk storage, comfortably accommodating the requirement. The need to scale to 5 instances requires a tier that can handle multiple instances reliably. Premium tier provides enhanced performance with DV2 series virtual machines and SSD storage. Premium offers better scaling capabilities and performance metrics compared to standard tier. While standard tier could handle the instance count, it cannot meet the storage requirements. Basic tier is insufficient as it only provides 10 GB storage and supports up to 3 instances. Question 2. What scaling option provides more CPU, memory, or disk space without adding more virtual machines? Answer. Scale up is the correct answer because scaling up, vertical scaling, increases the resources, CPU, memory, disk space, of existing virtual machines. This method involves moving to a higher pricing tier or more powerful compute instance. It doesn't add more VMs but rather enhances the capabilities of existing ones. This directly addresses the admin team's preference for increasing resource capacity without adding more VMs. Scale out, in contrast, would add more VM instances rather than increasing individual VM capacity. Scale back isn't a standard Azure scaling term and wouldn't provide additional resources. Question 3. Triggering a webhook at 8 a.m. on Saturday is what type of rule? Answer. A time-based rule. This is clearly a time-based rule because it's triggered based on a specific time and day, 8 a.m. on Saturday. Time-based rules are designed to handle scheduled events or recurring patterns. This type of rule doesn't rely on performance metrics or application load. It's perfect for predictable schedule-based scaling needs. Metric-based rules would instead respond to performance indicators like CPU usage or request queue length. App Insight rules isn't a standard category in Azure Autoscale rules. Key learning points. 1. When selecting an app service plan, carefully consider storage requirements along with other features. Basic, 10 GB storage. Standard, 50 GB storage. Premium, 250 GB storage too. Resource scaling comes in 2 forms. Scale up increases resources per VM, vertical scaling. Scale out adds more VMs, horizontal scaling. 3 autoscale rules are either time-based, for scheduled, predictable events. Metric-based, for performance-triggered, dynamic scaling. Understanding these distinctions helps in choosing the right service tier and scaling strategy for your specific requirements. Azure App Service represents a comprehensive platform that revolutionizes how we develop, deploy, and manage web applications. Let's explore the rich tapestry of benefits that make it a cornerstone of modern cloud application development. Starting with development flexibility, App Service truly shines in its multi-language support. Whether your team excels in ASP.NET, finds comfort in Java, or prefers the simplicity of Python, App Service accommodates all these languages and more. This flexibility extends to frameworks as well, making it a universal platform for diverse development needs. The seamless Visual Studio integration streamlines your development workflow, offering specialized tools for creation, deployment, and debugging. The DevOps capabilities in App Service transform how teams collaborate and deploy applications. Through native integration with popular platforms like Azure DevOps, GitHub, and Bitbucket, teams can implement robust continuous integration and deployment pipelines. This integration extends to container registries, supporting both Docker Hub and Azure Container Registry, enabling sophisticated containerization strategies. The ability to manage applications through PowerShell or the cross-platform CLI provides flexibility in automation and management approaches. When it comes to scale and reliability, App Service delivers impressive capabilities. The platform enables both manual and automatic scaling, allowing your applications to handle varying loads effectively. With Microsoft's global data center infrastructure at your disposal, you can host applications worldwide, ensuring optimal performance for users across different geographic locations. The platform's SLA provides peace of mind through guaranteed high availability. Connectivity features make App Service a truly versatile platform. With over 50 connectors available, you can integrate with enterprise systems like SAP, popular SaaS platforms like Salesforce, and social media services. The platform's hybrid connectivity options enable secure communication with on-premises resources through hybrid connections and Azure Virtual Networks, making it ideal for organizations with hybrid infrastructure requirements. Security and compliance receive paramount attention in App Service. The platform maintains compliance with crucial standards including ISO, SOC, and PCI, making it suitable for applications with strict regulatory requirements. Authentication options are comprehensive, supporting Microsoft Entra ID for enterprise scenarios and social login providers for consumer applications. IP address restrictions and managed service identities provide additional layers of security control. For rapid application development, App Service offers an extensive marketplace of application templates. Whether you're building a content management system with WordPress or developing a custom application, creating an application in Azure App Service involves a thoughtful progression through various configuration stages, each contributing to your application's functionality and performance. Let's explore this journey in detail. The process begins with establishing your application's identity. Your application needs a unique name that becomes part of its URL in the format applicationname.azurewebsites.net. This name serves as your application's digital address in the Azure ecosystem. While many organizations start with this default domain, you have the flexibility to map a custom domain name later, providing a more branded and professional appearance. Next comes the fundamental choice of your publishing model. App Service supports two primary approaches: deploying your application as code or as a Docker container. This decision shapes your deployment pipeline and maintenance strategies. Code deployment works well for traditional application development, while container deployment offers enhanced consistency across different environments and easier dependency management. The runtime stack selection represents a crucial technical decision. App Service supports a wide array of development frameworks and languages including .NET Core, Node.js, Python, PHP, and Ruby. Each stack comes with various version options, allowing you to match your application's specific requirements. For Linux applications and custom containers, you gain additional flexibility through optional startup commands or files, enabling fine-tuned control over your application's initialization process. Your choice of operating system between Linux and Windows influences both your application's runtime environment and available features. This decision should align with your application's requirements, your team's expertise, and your existing development practices. While both platforms offer robust support for modern web applications, certain framework versions or features might be specific to one operating system. Regional deployment represents a strategic decision affecting both performance and available features. Your chosen region influences which app service plans are accessible and impacts your application's latency for different geographic locations. This decision should balance various factors, including proximity to your user base, compliance requirements, and cost considerations. The App Service Plan selection defines your application's resource boundaries and available features. Think of this as choosing your application's hardware configuration and feature set. Different pricing tiers offer varying levels of computing power, storage capacity, and advanced features. The region you selected earlier determines which pricing tiers are available to you. Post-deployment configuration opens up additional optimization opportunities. The always-on feature prevents your application from becoming idle, ensuring consistent performance for scenarios like continuous web jobs or cron-triggered tasks. This setting proves particularly valuable for applications requiring constant availability and quick response times. For applications running on multiple instances, the ARR affinity setting becomes relevant. This feature ensures user sessions maintain consistency by routing requests to the same server instance throughout the session. While this can enhance user experience for certain applications, it should be used judiciously as it might impact load distribution. Security considerations are addressed through features like encrypted connection strings. These sensitive configuration values are protected both at rest and in transit, ensuring secure communication between your application and its dependencies. This encryption happens automatically, providing a robust security foundation without additional development effort. The configuration journey doesn't end with deployment. App Service provides ongoing flexibility to adjust settings as your requirements evolve. Through the Azure portal, you can modify deployment options, adjust path mappings, and fine-tune application settings. Many of these configurations can be managed either through the portal or programmatically, offering flexibility in your operational approach. Remember that while some configuration aspects can be embedded in your application code, others are better managed through App Service settings. This separation of concerns allows for environment-specific configurations without code changes, supporting robust deployment practices across development, staging, and production environments. Azure App Service offers a robust framework for implementing continuous integration and deployment, streamlining your application delivery pipeline from development to production. Let's explore the comprehensive deployment options available and how they can enhance your development workflow. Automated deployment represents the cornerstone of modern DevOps practices, enabling teams to deliver new features and fixes with unprecedented efficiency. At its heart, Azure DevOps integration provides a complete pipeline for your applications. Your development team pushes code to Azure DevOps, triggering an automated sequence of events: code compilation, test execution, release generation, and finally, deployment to your Azure web app. This seamless process ensures consistent, reliable deployments while maintaining code quality through automated testing. GitHub integration brings similar automation capabilities with additional collaboration features. When you connect your GitHub repository to Azure, any changes pushed to your production branch automatically flow through to your deployed application. This integration supports branch policies and pull request workflows, allowing teams to maintain code quality while automating deployment. The process becomes particularly powerful when combined with GitHub Actions, enabling sophisticated deployment scenarios and custom workflows. Bitbucket users aren't left behind, as Azure provides comparable automated deployment capabilities for Bitbucket repositories. This integration supports continuous deployment while maintaining the familiar Bitbucket workflow, making it an excellent choice for teams already invested in the Atlassian ecosystem. For teams preferring more control over their deployment process, manual deployment options provide flexible alternatives. Git deployment allows developers to treat their app service application as a remote Git repository. By adding the app service Git URL as a remote repository, developers can deploy updates with a simple git push command, maintaining familiar Git workflows while deploying directly to Azure. The Azure CLI offers a streamlined deployment experience through the web app up command. This powerful command handles multiple deployment steps in one operation, including creating a new app service web app if needed. It's particularly useful for scripting deployments or integrating with custom deployment tools. Visual Studio users benefit from a guided deployment experience through the App Service Deployment Wizard. This intuitive interface walks developers through the deployment process, handling configuration and deployment details, while providing visibility into the deployment progress. It's an excellent option for teams deeply integrated with the Visual Studio ecosystem. For situations requiring traditional file transfer methods, FTPS support ensures compatibility with existing deployment tools and workflows. While not as feature-rich as modern deployment methods, FTPS provides a reliable fallback option and can be particularly useful when dealing with legacy systems or specific file transfer requirements. The choice between automated and manual deployment often depends on your team's size, development practices, and release requirements. Automated deployment shines in scenarios requiring frequent updates, multiple developers, or complex testing requirements. The consistent, repeatable nature of automated deployments reduces human error and ensures all necessary steps are completed in the correct order. Manual deployment methods offer greater control and simplicity for smaller teams or projects with less frequent updates. They can also serve as a valuable backup option when automated systems require maintenance or troubleshooting. The key is selecting the deployment method that best aligns with your team's capabilities and project requirements. Each deployment method integrates seamlessly with Azure App Services features, such as deployment slots for staging environments and rollback capabilities for managing deployment issues. This integration ensures you can maintain high availability while deploying updates, regardless of your chosen deployment method. Remember that these deployment options aren't mutually exclusive. Many teams implement a hybrid approach, using automated deployment for their main development pipeline while maintaining manual deployment capabilities for special cases or emergency updates. This flexibility ensures your deployment strategy can adapt to changing project requirements and team needs. Deployment slots in Azure App Service represent a powerful feature that transforms how we manage application updates and maintain high availability. Let's explore the intricacies of deployment slots and understand how they can enhance your deployment strategy. At their core, deployment slots are live applications with their own host names, running independently from your production environment. Think of them as parallel universes for your application, each capable of running different versions of your code. This capability is available exclusively in the standard, premium, and isolated app service pricing tiers, with each tier offering different numbers of deployment slots to match your needs. The validation process becomes significantly more robust with deployment slots. Instead of deploying changes directly to production, you can push updates to a staging slot first. This approach creates a safe space to validate your changes, run integration tests, and ensure everything functions as expected before affecting your live users. The staging environment perfectly mirrors your production setup, providing accurate testing conditions. One of the most compelling benefits of deployment slots is their ability to eliminate deployment downtime. When you're ready to move changes to production, the slot swapping process ensures all instances are properly warmed up before the swap occurs. This warm-up period is crucial as it allows your application to load all necessary components and establish required connections. The result is a seamless transition that maintains continuous availability for your users. The swap operation itself is an elegant solution to deployment challenges. When you initiate a swap, App Service exchanges the content and configurations between two slots. This exchange happens instantaneously, and the traffic redirection is handled so smoothly that no requests are dropped during the process. It's like changing the engine of a car while it's running, but without any interruption in performance. For teams embracing automated deployment practices, the Auto Swap feature presents a compelling option. When enabled, Auto Swap automatically moves your changes to production after successful deployment and warm-up in the source slot. This automation streamlines your continuous deployment pipeline, particularly valuable in Azure DevOps scenarios. However, it's important to note that AutoSwap isn't currently available for web apps on Linux. Perhaps one of the most reassuring aspects of deployment slots is their built-in safety net for production issues. If unexpected problems arise after a swap, you can immediately perform another swap to revert to your previous production version. This capability to return to your last known good site provides peace of mind and significantly reduces the risk associated with deployments. The configuration flexibility of deployment slots adds another layer of sophistication to your deployment strategy. You can maintain specific settings for each slot while sharing others across all slots. This granular control allows you to manage environment-specific configurations effectively while maintaining consistency where needed. When implementing deployment slots, consider creating a systematic approach to your deployment workflow. Deploy updates to a staging slot. Validate the changes in the staging environment. Warm up the application in the staging slot swap. The slots when ready. Verify the production environment after the swap. Keep the previous production version ready in staging for potential rollback. This methodical approach, combined with the features of deployment slots, creates a robust and reliable deployment process that minimizes risk and maximizes application availability. Whether you're running a small business application or a large-scale enterprise system, deployment slots provide the tools needed to manage updates with confidence and precision. Remember that while deployment slots are powerful, they require appropriate planning and resource allocation. Each slot runs an active copy of your application, consuming resources from your app service plan. Factor this into your capacity planning to ensure optimal performance across all slots. Understanding the intricacies of deployment slot settings is crucial for effectively managing your Azure App Service deployments. Let's explore how these settings work and how they impact your deployment strategy. When creating new deployment slots, you have two initialization options, starting with an empty slot or cloning configuration from an existing slot. This flexibility allows you to build your deployment environment according to your specific needs. An empty slot provides a clean slate, while cloning brings over selected settings from another slot, accelerating the setup process. Deployment slot settings fall into three fundamental categories. First, you have slot-specific application settings and connection strings, which can be configured to remain with specific slots during swaps. Second, continuous deployment settings manage how your application updates are deployed when enabled. Third, Azure App Service authentication settings control how your application handles user authentication and authorization. The way settings behave during slot swaps follows a carefully designed pattern. Some settings move with your application content during a swap, while others remain fixed to their original slots. This distinction is crucial for maintaining proper application configuration across environments. Settings that swap between slots include general framework configurations, such as runtime versions and WebSocket settings, handler mappings that define URL routing, public certificates for secure communications, WebJobs content for background processing, hybrid connections for secure on-premises connectivity, service endpoints for network integration settings that stay with their original slots. Slot-specific include custom domain names and SSL bindings, scale settings controlling instance count and size, IP restrictions for access control, diagnostic configurations for monitoring, cross-origin resource sharing, CORS, settings, virtual network integration parameters, managed identities for secure access to Azure Resources app settings and connection strings deserve special attention as they can be configured either way. By default, these settings swap with your application, but you can mark specific ones as slot-specific. This flexibility is particularly valuable for maintaining environment-specific configurations while allowing other settings to move with your application code. When planning your slot strategy, consider these practical implications. Environment-specific settings. Use slot-specific settings for configurations that should never swap, such as database connection strings for development versus production environments. Security configurations. Keep security-related settings like SSL certificates and IP restrictions slot-specific too. Maintain proper security boundaries between environments. Scaling requirements. Since scale settings are slot-specific, you can optimize resource allocation differently for each slot, while maintaining the ability to swap application code. Monitoring and diagnostics. Each slot can maintain its own diagnostic settings, enabling environment-specific monitoring without affecting other slots during swaps. The cloning process for configurations provides additional flexibility. When you clone settings from another slot, you're not creating an immutable copy. The cloned configuration remains editable. This allows you to start with a known configuration and customize it for specific needs. Extension settings, identified by the suffix extension version, always remain with their specific slots. This ensures that extension configurations don't unexpectedly change during slot swaps, maintaining stability in your extended functionality. For optimal slot management, carefully document which settings are configured as slot-specific. Maintain a clear naming convention for slot-specific settings. Regularly review and update slot configurations as your application evolves. Test slot swaps in non-production environments first to verify setting behavior. Remember that while deployment slots offer powerful configuration flexibility, they require thoughtful planning to use effectively. The key is to strike the right balance between settings that should move with your application and those that should remain fixed to specific environments. Azure App Service provides a robust built-in security framework that simplifies the implementation of authentication and authorization in your applications. Let's explore how this security infrastructure works and how it can protect your applications effectively. The security architecture in App Service is ingeniously designed. The authentication and authorization module operates in the same environment as your application, but runs independently from your application code. This separation of concerns means you can implement comprehensive security without modifying your application's core functionality. The module is configured through app settings, eliminating the need for specific SDKs or language-dependent implementations. The security workflow is straightforward yet powerful. Every incoming HTTP request passes through the security module before reaching your application code. This module handles several critical security tasks automatically. Authentication process validates user credentials against specified providers, manages token lifecycle, validation, storage, refreshing, maintains authenticated sessions securely, injects identity information into request headers. You have two primary options for handling authentication in your app service applications. One-pod anonymous access mode allows unauthenticated traffic to reach your application. Passes authentication information in HTTP headers for authenticated requests. Provides flexibility for handling different authentication scenarios. Enables support for multiple sign-in providers. Ideal for applications requiring public access to certain features, authenticated only mode. Redirects all anonymous requests to the authentication endpoint. Returns HTTP 401, unauthorized for anonymous mobile app requests. Eliminates need for custom authentication code. Provides complete access control at the platform level. Perfect for applications requiring strict security. The logging and monitoring capabilities enhance your security oversight. The system provides detailed authentication and authorization traces directly in your application logs. When investigating security-related issues, you can examine failed request traces, looking specifically for the EasyAuth module or 3264 module's activities. This visibility helps you quickly identify and resolve security concerns. Implementation. Considerations. For public-facing applications, consider using anonymous access mode if you need a public landing page. Implement custom authentication logic for specific routes. Utilize multiple authentication providers for user flexibility. Configure appropriate redirect URLs for authentication. Implement proper token handling for mobile clients. For monitoring and maintenance, enable comprehensive logging for security events. Set up alerts for authentication failures. Regularly review security traces and logs. The beauty of this security framework lies in its flexibility. While App Service provides these robust security features, you're not locked into using them. If your application already implements security through its framework, or you prefer a different authentication service, you can continue using those methods. Best practices for implementation. Security configuration. Start with the most restrictive security model appropriate for your application. Configure authentication providers thoroughly. Set appropriate token lifetimes and refresh policies. User experience. Design. Clear authentication flows. Provide appropriate feedback for authentication failures. Implement smooth transitions between authenticated and public areas monitoring. Enable detailed logging for security events. Set up alerts for suspicious activities. Regularly review security logs and traces maintenance. Keep authentication providers updated. Review and update security policies regularly. Monitor for new security features and updates. Remember that while App Service security simplifies authentication and authorization, it's crucial to maintain secure coding practices and regularly review your security implementation to ensure it meets your application's evolving needs. Creating a professional online presence often requires moving beyond the default Azure Websites.net domain to a custom domain name. Let's explore how to effectively implement custom domains in Azure App Service. Before diving into the configuration process, it's crucial to note that custom domain support requires a paid tier of App Service plan. This requirement ensures your application has access to the necessary infrastructure for proper domain management and SSL support. The process of setting up a custom domain involves three main steps, each playing a vital role in establishing your professional web presence. Step 1. Domain name reservation. The most straightforward approach is purchasing your domain directly through the Azure portal. This integration offers several advantages. Seamless management of domain settings within the Azure ecosystem. Simplified configuration process for connecting to your web app. Centralized billing and renewal management. Direct support from Microsoft for domain-related issues. While you can use domains purchased from third-party registrars, the Azure integrated approach streamlines the entire process by eliminating the need to juggle multiple service providers. Step 2. DNS record configuration. This critical step establishes the connection between your domain name and your Azure web app. You have two primary options for DNS records. A records, address records, directly maps your domain to an IP address. Provides straightforward configuration. Requires updates if the IP address changes. Often necessary for root domains. Useful when CNAME records aren't allowed. CNAME records, canonical name, maps your domain to another domain name, your Azure Websites.net URL. Maintains validity even if the underlying IP address changes. Provides more flexibility for future changes. May not be supported for root domains by all registrars. Ideal for subdomains and www prefixes. The choice between A and CNAME records often depends on your specific requirements and registrar limitations. While CNAME records offer more flexibility, some domain registrars restrict their use for root domains or wildcard domains, necessitating the use of A records. Step 3. Domain enablement. The final step involves validating and activating your custom domain. Verify domain ownership through the Azure portal. Add the domain to your web app configuration. Test the domain thoroughly before public release. Configure any additional settings like SSL certificates, best practices for custom domain. Implementation planning phase. Choose appropriate record types based on your needs. Consider future scaling requirements plan for SSL certificate implementation document all configuration changes. Testing requirements. Verify DNS propagation test domain. Accessibility confirm. SSL certificate functionality. Check application behavior with new domain maintenance considerations. Monitor domain registration expiration. Keep DNS records updated. Regular validation of SSL certificates. Periodic testing of domain functionality. Security implications. Implement SSL certificates. Promptly configure proper redirect rules. Monitor for unusual domain activity. Maintain secure DNS configurations. Remember that DNS changes can take time to propagate across the Internet. This propagation delay, which can range from a few minutes to 48 hours, means you should plan your domain transition accordingly and maintain both old and new configurations during the transition period. For applications requiring multiple domains or subdomains, ensure your app service plan supports the number of custom domains you need. Different tiers have different limits on the number of custom domains they support. Regular monitoring and maintenance of your custom domain configuration ensures continued accessibility and security of your web application. Keep track of domain registration renewals, SSL certificate expiration dates, and any changes to your DNS configuration to maintain a professional and reliable web presence. Azure App Services backup and restore functionality provides a robust solution for protecting and recovering your application data. Let's explore the comprehensive features and implementation considerations of this essential service. First, it's important to note that this feature requires either a standard or premium tier app service plan. This requirement ensures your application has access to the necessary infrastructure for reliable backup operations. Additionally, you'll need an Azure storage account and container within the same subscription as your application to store the backups. The backup capability is remarkably comprehensive, encompassing application components, all configuration settings, complete file content, connected databases, SQL database, Azure database for MySQL, PostgreSQL, and in-app MySQL. 2. Storage structure. Each backup creates 2 essential files. A zip file containing all backup data. An XML file serving as a manifest of the zip contents. Maximum backup size of 10 GB for app and database content combined. The system offers 2 distinct backup approaches. Full backups default, captures entire application state. Includes all configuration settings. Backs up all file content. Stores complete database content. Ideal for comprehensive recovery needs, partial backups. Allows specific file and folder selection. Enables exclusion of unnecessary content. Maintains existing content during restoration. Perfect for targeted backup requirements. Backup scheduling provides flexible options. Manual backups for immediate needs. Scheduled backups for automated protection. Configurable retention periods. Options for indefinite storage implementation considerations. 1. Storage requirements. Verify storage account accessibility. Check firewall configurations. Ensure sufficient storage capacity. Monitor backup sizes. The backup strategy. Choose between full and partial backups. Set appropriate backup frequencies. Define retention policies. Document excluded content. Restore planning. Understand content replacement implications. Plan for partial restore scenarios. Test restore procedures regularly. Maintain access permissions. Best practices for implementation. Regular testing. Verify backup integrity. Practice restore procedures. Validate database recovery. Check excluded content handling. 2. Documentation. Record backup configurations. List excluded content. Document restore procedures. Maintain change. Logs. 3. Monitoring. Track backup completion status. Monitor storage usage. Verify schedule execution. Check retention policy enforcement. Important considerations. Storage. Firewall. Ensure firewall settings allow backup operations. Configure necessary access rules. Verify connectivity regularly. Plan for security changes. Content management. Understand full backup. Replacement behavior plan partial. Backup strategies carefully. Consider file exclusion impacts, manage database backup requirements, recovery scenarios. Browse backup content. Without restoration plan, for different recovery needs, test various restore scenarios. Document recovery procedures, maintenance tasks. Review backup configurations regularly. Update exclusion lists as needed. Monitor storage capacity. Verify backup success. Remember that while backups provide essential protection, they should be part of a broader disaster recovery strategy. Consider implementing additional measures such as geographic redundancy, multi-region deployment, regular security updates, comprehensive monitoring. By carefully planning and implementing your backup strategy, you can ensure your application's data is protected and recoverable when needed. Regular testing and maintenance of your backup and restore procedures will help maintain their effectiveness and reliability over time. Azure Application Insights transforms how we monitor and understand application performance and user behavior. As an integral feature of Azure Monitor, it provides deep insights into your application's operation, helping development teams make data-driven decisions for continuous improvement. Platform versatility. Application Insights demonstrates remarkable flexibility in its platform support. Whether you're working with .NET applications, Node.js services, or Java EE systems, the monitoring capabilities remain consistent and powerful. This cross-platform support extends to both cloud-hosted and on-premises applications, making it an ideal choice for hybrid environments. Integration with Visual Studio App Center brings these powerful monitoring capabilities to mobile applications as well. Key monitoring capabilities. Request performance. Monitoring. Track request rates and patterns. Measure response times across different endpoints. Identify failure rates in problematic areas. Correlate traffic patterns with performance metrics. Detect resource bottlenecks during high load periods. 2. Dependency analysis. Monitor external service interactions. Track dependency response times. Identify failing dependencies. Measure impact on application performance. Map service dependencies for better architecture understanding. 3. Exception tracking. Capture both server and browser exceptions. Access detailed stack traces. Correlate exceptions with specific requests. Aggregate error statistics. Identify patterns in exception occurrence. 4. User experience. Insights. Monitor page view statistics. Analyze page load performance. Track user and session counts. Understand user navigation patterns. Measure client-side performance metrics. 5. Server performance monitoring. Track CPU utilization. Monitor memory consumption. Analyze network usage patterns. Observe disk performance. Monitor custom performance counters. 6. Advanced diagnostics. Integrate Docker diagnostics. Access host-level metrics. Review diagnostic trace logs. Correlate events across services. Track custom business metrics. Implementation best practices. Monitoring strategy. Define key performance indicators. Set up appropriate alerting thresholds. Configure custom events for business metrics. Implement comprehensive exception handling. Establish baseline performance metrics. Performance optimization. Monitor page load. Times track dependency response times. Analyze server response patterns. Identify performance bottlenecks. Implement performance improvements. User analysis. Track user engagement, metrics, Analyze session patterns, monitor feature usage, understand user behavior, measure business outcomes, operational excellence, set up proactive alerts, monitor resource utilization, track deployment impacts, analyze performance trends, maintain monitoring coverage, custom tracking. Implementation. Application Insights allows you to extend its capabilities through custom events and metrics. This flexibility enables tracking of business-specific events, custom performance metrics, user interaction patterns, feature adoption rates, business outcome measurements. Development integration. The service integrates seamlessly with development workflows. Direct Visual Studio integration, DevOps pipeline compatibility, continuous monitoring support. Deployment impact analysis, development team collaboration. By leveraging these comprehensive monitoring capabilities, development teams can identify issues before they impact users, understand application performance patterns, make data-driven optimization decisions, track the impact of changes, maintain high application quality. Remember that effective monitoring requires ongoing attention and refinement. Regularly review your monitoring strategy, adjust metrics and thresholds based on application evolution, and ensure your team makes full use of the insights provided by Application Insights for continuous improvement of your application's performance and user experience. Let's analyze each question and understand the correct answers with detailed explanations. Question 1. When you clone a configuration from another deployment slot, which configuration setting follows the content across the swap? Answer: connection strings. Explanation. Connection strings are part of the swapped settings that follow content across deployment slot swaps. Here's why. Connection strings are considered part of the application configuration that should move with the application. This ensures database connections remain consistent with the application version. Other settings mentioned in the options are slot-specific. Custom domain names stay with the slot to maintain DNS stability. Scale settings remain slot-specific to maintain appropriate resource allocation. This separation allows different environments to maintain their specific configurations. Question 2. How can you support the marketing team requests about research web page usage? Answer: Azure Application. Insights. Explanation. Azure Application. Insights is the ideal solution for the marketing team's requirements because it provides comprehensive user behavior analytics including page view statistics, time-based usage patterns, geographic location of users, user session tracking, performance metrics. Other options wouldn't provide the necessary insights. Continuous deployment focuses on code deployment automation. Application logging primarily tracks technical operations. Application Insights specifically offers real-time user behavior tracking, detailed analytics and reporting, geographic distribution analysis, usage pattern visualization. Question 3. Which option is a valid automated deployment source? Answer: GitHub. Explanation: GitHub is a valid automated deployment source for Azure App Service because it integrates directly with Azure App Service's continuous deployment features, provides automated deployment triggered by repository changes, supports various deployment configurations, branch-based deployment, pull request workflows, automated testing integration. The other options are not valid automated deployment sources. JavaScript code is a programming language, not a deployment source. SharePoint is a collaboration platform, not a source control system. Key learning points: 1. Deployment slot configuration. Understanding which settings swap and which remain slot-specific. Importance of connection string behavior in deployment scenarios. Role of slot-specific settings in maintaining environment stability. 2. Analytics and monitoring. Matching business requirements with appropriate monitoring tools. Understanding application insights capabilities for user behavior analysis, importance of proper monitoring for marketing insights, automated deployment, recognizing valid deployment source options. The evolution of virtualization technology has brought us two powerful approaches to resource isolation and management: containers and virtual machines. Let's explore their key differences and understand when to use each technology. Isolation characteristics. Containers provide lightweight OS-level isolation. Share the host operating system kernel. Maintain separation between applications. Offer faster startup and lower resource overhead. Present a lighter security boundary. Virtual machines deliver complete hardware-level isolation. Run independent operating system instances. Provide stronger security boundaries. Ideal for multi-tenant environments. Perfect for scenarios requiring complete isolation. Operating system. Implementation. Containers. Run only the user mode portion of the OS. Include minimal required services. Optimize resource utilization. Enable rapid deployment and scaling. Reduce system overhead. Virtual machines run complete operating systems. Include full kernel operations. Require more system resources. Support diverse operating systems. Provide full OS functionality. Deployment mechanisms. Containers. Deploy via Docker command line. Orchestrate with Kubernetes. Support rapid scaling. Enable automated deployment. Facilitate continuous delivery. Virtual machines. Deploy through Windows Admin Center. Manage via Hyper-V. Orchestrate with System Center. Support PowerShell automation. Enable traditional deployment patterns. Storage solutions. Containers. Utilize Azure disks for local storage. Leverage Azure files for shared storage. Support ephemeral storage patterns. Enable data persistence across instances. Facilitate storage orchestration. Virtual machines. Use virtual hard disks, VHD. Support SMB file shares. Provide traditional storage patterns. Enable direct storage access. Support various storage protocols. Fault tolerance approaches. Containers. Enable rapid recreation on node failure. Support automatic orchestration. Provide quick service recovery. Facilitate stateless applications. Enable high availability patterns. Virtual machines. Support traditional failover clustering. Enable OS-level recovery. Provide complete state preservation. Support stateful applications. Maintain system consistency. Implementation. Considerations. Resource efficiency. Containers excel in resource utilization. VMs provide complete environment isolation. Container density typically higher than VMs. VM overhead includes full OS resources. Container sharing reduces resource requirements. Security requirements. VMs offer stronger security boundaries. Containers provide application-level isolation. VM isolation suitable for competing workloads. Container security requires careful configuration. VM security benefits from complete isolation deployment. Speed. Containers enable rapid deployment. VMs require more time for initialization. Container orchestration provides quick scaling. VM deployment involves full OS provisioning. Container images optimize deployment time. Management complexity. Container orchestration requires specialized knowledge. VM management follows traditional patterns. Container ecosystems need orchestration platforms. VM management uses familiar tools. Container management scales differently. Choosing between containers and VMs. Use containers when rapid deployment is crucial. Resource efficiency is primary concern. Applications are cloud-native. Microservices architecture is implemented. Development and operations need streamlining. Use virtual machines when complete isolation is required. Traditional applications need hosting. Full OS functionality is necessary. Strong security boundaries are crucial. Legacy systems need support. Best practices for implementation. Hybrid approaches. Consider running containers on VMs. Leverage strengths of both technologies. Implement appropriate security levels. Balance resource utilization. Enable flexible deployment options, monitoring and management. Implement appropriate monitoring tools. Consider orchestration requirements. Plan for scaling needs. Prepare for fault tolerance. Establish management procedures. Understanding these differences helps in making informed decisions about which technology best suits specific use cases, while maintaining optimal performance and security. Containers represent a revolutionary approach to application deployment and management, offering significant advantages over traditional deployment methods. Let's explore their benefits and understand the structure of container images that make these benefits possible. Key benefits of containers: flexibility and speed, rapid development cycles enabled by consistent environments, quick sharing of containerized applications across teams, immediate environment replication for development, fast iteration and testing cycles, efficient code modification and deployment. 2. Simplified testing, consistent test environments across development stages. Identical configurations from development to production, easy reproduction of production issues, reliable testing processes, reduced environment-related bugs, streamlined deployment, accelerated application deployment process, consistent deployment across different platforms, automated deployment workflows, reduced deployment-related errors, efficient scaling capabilities. 4. Workload density, improved resource utilization, higher application density per host, optimized infrastructure costs, efficient resource sharing, better server utilization, container image components, when application code, source code of the application, required dependencies, build artifacts, static assets, documentation, Dart runtime environment, execution platform, language runtime, framework dependencies, development tools, debugging utilities, system tools and libraries, essential system utilities, shared libraries, system dependencies, common tools, support utilities, taught configuration settings, environment variables, configuration files, application parameters, runtime settings, service connections, implementation considerations, image design, keep images lightweight, include only necessary components, layer optimization, security considerations, version control to taunt development, workflow, consistent development environments, rapid iteration cycles, integrated testing, continuous integration, automated builds. 3. Deployment strategy, orchestration requirements, scaling considerations, resource allocation, network configuration, storage management, maintenance practices, regular updates, security patches, performance optimization, monitoring setup, backup procedures, best practices for container, implementation, image management, use official base images, implement proper versioning, regular security updates, optimize layer ordering, document image contents, development process, implement CI/CD pipelines, automated testing, version control integration, code review processes, environment parity, operational considerations, resource monitoring, performance optimization, security scanning, backup strategies, disaster recovery team, collaboration, shared repositories, documentation, standards, knowledge sharing, training programs, best practices. The portability of container images ensures consistent application behavior across different environments. Development benefits: identical development environments, quick onboarding of new developers, reduced environment setup time, consistent testing conditions, improved collaboration. Operational benefits: reliable deployments, simplified scaling, efficient resource usage, easy environment replication, reduced operational overhead. Business benefits: faster time to market, reduced infrastructure costs, improved application reliability, enhanced team productivity, better resource utilization. By understanding and implementing these container concepts effectively, organizations can significantly improve their application development and deployment processes while maintaining consistency and reliability across their infrastructure. Azure Container Instances (ACI) represents a groundbreaking approach to container deployment in the cloud, offering a streamlined solution for running containers without the complexity of managing virtual machines or orchestration systems. Let's explore the comprehensive features and benefits that make ACI an attractive choice for various containerization scenarios. Core features and benefits: rapid deployment, instant container startup without VM provisioning, simplified deployment process, no infrastructure management overhead, quick scaling capabilities, immediate resource availability network, connectivity, automatic public IP address assignment, built-in FQDN, support direct internet exposure capabilities, DNS name management, simplified network configuration, resource flexibility, dynamic resource scaling, custom container sizing, efficient resource allocation, pay-per-second billing resource, optimization capabilities, storage solutions, Azure Files integration, persistent storage support, direct file share mounting, data persistence across instances, shared storage capabilities, platform support, Windows container compatibility, Linux container support, mixed environment deployment, cross-platform capabilities, flexible operating system choice, implementation scenarios, simple applications, web applications, API services, background job scheduled tasks, testing environments, task, automation, batch processing, data analysis, report generation, scheduled maintenance, system updates, build, jobs, continuous integration, automated testing, code compilation, documentation generation, artifact creation, deployment considerations, resource management, CPU allocation, memory requirements, storage configuration, network settings, container group organization, network, integration, virtual network, deployment, network security, traffic routing, access control, DNS configuration, multi-container groups, resource sharing, inter-container communication, shared lifecycle management, coordinated deployments, group scaling, best practices, performance optimization, right-size containers, optimize resource allocation, monitor usage patterns, implement, auto-scaling, regular performance reviews, security implementation, network isolation, access control, secret management, image, security, regular updates, cost management, resource monitoring, usage optimization, scaling strategies, budget control, cost allocation, operational benefits, simplified management, no VM maintenance, automated updates, streamlined deployment, reduced complexity, easy monitoring, development efficiency, rapid prototyping, quick testing, easy environment, replication, fast iterations, simplified debugging, resource optimization, pay-per-use model, efficient resource utilization, dynamic scaling, cost effectiveness, resource sharing, integration, capabilities, Azure services, Azure files, virtual networks, Azure Monitor, Azure Identity, Azure DevOps, development tools, Azure, Clearest APSDK, support templates, PowerShell. By leveraging these features and capabilities, organizations can efficiently deploy and manage containerized applications while focusing on application development rather than infrastructure management. ACI provides the perfect balance of simplicity and functionality for scenarios that require isolated container deployment without the complexity of full orchestration systems. Azure Container Groups represent a fundamental building block in Azure Container instances, providing a logical boundary for deploying and managing multiple containers as a single unit. Let's explore the comprehensive features and implementation details of container groups. Core concepts. 1. Container group structure. Similar to Kubernetes pods. Multiple containers on single host. Shared resource environment. Coordinated lifecycle management. Unified networking space. 2. Resource sharing. Aggregated resource allocation. Common network namespace. Shared storage volumes, combined lifecycle management, unified DNS and IP addressing, resource management, 1 compute resources, CPU allocation adds across containers, memory requirements combined, GPU resource sharing, resource limits apply to group, balanced distribution, .network configuration, single IP address per group, shared port namespace, common DNS label, external client access, port exposure requirements, deployment methods. 1. ARM templates. Recommended for complex deployments, Azure Service Integration, resource dependency management, template-based configuration, infrastructure as code, 2 YAML files, simplified configuration, container-focused deployments, concise syntax, easy maintenance, quick modifications, implementation considerations, resource planning, calculate total resource needs, consider container interactions, plan storage requirements, network capacity planning, scaling considerations, 2 network management, port mapping limitations, external access configuration, DNS label management, IP address, lifecycle, security considerations, 3 storage configuration, volume sharing setup, persistent storage needs, access permissions, data lifecycle, backup strategies, best practices, group organization, logical container grouping, resource optimization, clear naming conventions, proper documentation, monitoring setup, 2-point deployment strategy, choose appropriate deployment method, version control configurations, testing procedures, rollback planning, update strategies, pod resource optimization, right-size resource requests, monitor usage patterns, optimize configurations, cost management, performance tuning, operational guidelines, lifecycle management, coordinated deployments, group-wide updates, synchronized scaling, consistent monitoring, unified logging, 2. Access control, port exposure management, security configurations, authentication setup, authorization rules, network policies, 3. Monitoring and maintenance, group-level metrics, resource utilization tracking, performance monitoring, regular updates, health checks, integration scenarios, application, architecture, microservices, deployment, sidecar patterns, helper containers, monitoring agent, service mesh, integration infrastructure, integration, Azure Services Connection, storage solutions, networking, setup, monitoring, integration, security services, key limitations, port mapping, no support for port mapping, shared port namespace, port conflict management, access coordination service, exposure planning, resource release, IP address release on deletion, FQDN, availability, resource cleanup, state management, data persistence. By understanding these aspects of container groups, organizations can effectively implement and manage multi-container deployments in Azure container instances, ensuring optimal resource utilization and operational efficiency while maintaining proper isolation and coordination between containers. Azure Container Groups enable sophisticated multi-container scenarios through careful configuration and resource sharing. Let's explore a practical example configuration and various implementation scenarios that demonstrate the power and flexibility of container groups. Example: configuration, analysis, infrastructure, setup, single host machine deployment, unified DNS name label assignment, shared public IP address coordinated port management, integrated storage configuration, network configuration, shared public IP address, port 80 for web traffic, port 1433 for database access, coordinated port exposure, internal communication paths, storage implementation. 2. Azure Files shares individual container mounting, persistent storage access, isolated data spaces, shared resource management, practical implementation scenarios. Web application, updates, content delivery, configuration, main container, web application server, secondary container, content updater, automated content, synchronization version, control integration, zero downtime updates logging, implementation data collection, strategy application container, generates logs, logging container, processes, data persistent storage writing metrics collection, long-term data retention application, monitoring health check system, primary container, application service, monitor container, health checker, regular status verification, alert generation, performance tracking, full stack applications, service architecture, front-end container, user interface, back-end container, data services, internal communication, resource sharing, coordinated scaling, implementation best practices, resource planning, calculate combined requirements, plan port allocations, configure storage needs set, memory limits, define CPU quotas, network configuration, port exposure strategy, internal communication setup, DNS configuration, security rules, load balancing, storage management, volume mount planning, access permissions, backup strategies, data lifecycle, performance optimization, operational considerations, deployment strategy, version control update, procedures rollback, planning configuration management, monitoring setup, maintenance procedures, regular updates, health checks, performance monitoring, log analysis, security patches, scaling considerations, resource requirements, performance metrics, load patterns, cost optimization, capacity planning, use, case benefits, web application scenario, automated content updates, simplified deployment, consistent environments, efficient resource use, improved maintenance logging. Solution: centralized log collection, efficient data processing, reliable storage, easy analysis, scalable architecture monitoring. Setup: real-time health checks, proactive issue detection, automated alerts, performance insights, quick response capability. Full stack implementation, simplified architecture, efficient communication, resource optimization. Easy management, coordinated updates, advanced configuration tips, resource optimization, right-size containers, optimize resource sharing, monitor usage patterns, adjust limits, balance workloads, security enhancement, network isolation, access, control secure communication, data protection, monitoring, integration, performance, tuning, resource allocation, communication efficiency, storage optimization, network configuration, cache implementation. By understanding these configuration patterns and use cases, organizations can effectively implement container groups to support various application scenarios while maintaining optimal performance and resource utilization. Azure Container Apps represents a significant evolution in containerized application deployment, offering a serverless platform that simplifies infrastructure management while providing powerful capabilities for modern application architectures. Let's explore its comprehensive features and implementation scenarios. Core platform features. 1. Serverless architecture. Automated infrastructure management, pay-per-use pricing model. 0. Infrastructure maintenance. Automatic scaling capabilities. Built-in orchestration. 2. Microservices support. Service discovery mechanisms. Traffic splitting capabilities. Inter-service communication. Load balancing. Version management. 3. Event-driven processing. Queue-based scaling. Event source integration. Background job support. Asynchronous processing. Message handling. Dynamic scaling capabilities. HTTP traffic. Scaling. Request-based autoscaling. Load pattern adaptation. Traffic management. Resource optimization. Zero-scale support. 2. Resource-based scaling. CPU utilization monitoring, memory usage tracking. Performance-based scaling. Resource threshold management. Automatic adjustments. 3. KEDA. Integration. Multiple scalar support. Custom metric scaling. Event-driven autoscaling. Queue length monitoring. Scheduled scaling implementation scenarios. API endpoints. RESTful services. GraphQL endpoints. WebSocket support. API versioning. Traffic management. 2. Background processing. Batch operations. Data processing. Scheduled tasks. Resource-intensive operations, long-running jobs. Event processing. Message queue handlers. Event-driven workflows. Real-time processing. Asynchronous operations. Stream processing. Technology integration. Kubernetes. Foundation. Container orchestration. Service management. Resource allocation. Health monitoring, deployment control. Dapper integration. Service invocation. State management. Pub/sub messaging. Resource bindings. Distributed tracing. 3. Envoy. Proxy. Traffic management. Load balancing. Service mesh capabilities. Security features. Request routing, operational benefits. Infrastructure management. Reduced complexity. Automated updates. Security management. Resource optimization. Cost efficiency to development experience. Simplified deployment, built-in tooling. CI/CD integration. Development workflows, version control. 3. Scalability. Features. Automatic scaling. Resource optimization. Performance management. Cost control. Load handling. Best practices. Application design. Microservices. Architecture event-driven patterns. Stateless design service composition. Error handling resource management. Scaling configurations. Resource allocation performance monitoring cost optimization capacity. Planning security. Implementation. Authentication setup. Authorization rules network. Security data protection compliance management. When to choose container apps. Ideal scenarios. Microservices deployment. Event-driven applications. API implementations, background processing, scheduled jobs consideration factors. Infrastructure requirements. Scaling needs management preferences, budget constraints. Technical expertise. By leveraging Azure Container Apps, organizations can focus on application development while letting the platform handle infrastructure management, scaling, and operational concerns. This approach enables faster development cycles, reduced operational overhead, and more efficient resource utilization for containerized applications.